Please subscribe to support the channel. When a headline claims that the James Webb Space Telescope has found a planet with a 99.7% chance of life, it instantly demands attention. This isn't just another space story. It's the kind of announcement that challenges our understanding of the universe and our place within it. For centuries, humanity has looked up at the night sky and wondered, are we alone? Every new telescope, every scientific breakthrough, every discovery of a star system or a strange new planet inches us closer to an answer. But this claim about K2-18b doesn't just inch us closer, it feels like a giant leap. A percentage that high, 99.7%, is nearly absolute certainty. And if true, it would mean that alien life is no longer the stuff of science fiction, it's a scientific reality. But the sheer boldness of this claim is exactly why it's so groundbreaking. For decades, scientists have been extremely cautious in their wording. They talk about potential habitability, possible biosignatures, and intriguing signals. Rarely, if ever, do you hear researchers attach such a precise probability, especially one as high as 99.7%. So, when the story about K2-18b erupted, it wasn't just about another exoplanet. It was about a potential paradigm shift. Why does this matter so much? Because if life exists on K2-18b, then life in the universe is not rare, and perhaps it is not even unusual. It would mean the conditions necessary for biology are more common than we once believed. It would mean that in the vastness of space, there could be countless other planets teeming with microbes, ecosystems, or maybe even civilizations. The discovery of life beyond Earth would rank as one of the most profound milestones in human history, on par with learning that Earth orbits the Sun, or that DNA encodes life itself. But such a claim also comes with weight. A 99.7% probability of life isn't just a scientific statement, it's an invitation to reimagine our place in the cosmos. It sparks questions. How was this number determined? Is it really science, or is it interpretation, perhaps even exaggeration? What kind of life are we even talking about here? Are we imagining intelligent beings, or something far more humble, like microbial life floating in an alien ocean? The claim is groundbreaking because it takes the conversation beyond mere speculation. It forces us to grapple with possibilities we've only whispered about until now. What if we are on the brink of confirming that life is not unique to Earth? What if this is the first domino to fall in a cascade of discoveries that reveal a universe brimming with living worlds? But before we rush ahead, we need to ground ourselves in what we know, what we've observed, and what remains uncertain. The headline is powerful, but the story behind it is even more fascinating. To understand why K2-18b has captured the world's imagination, we need to step back and look at the tool that made this claim possible, the James Webb Space Telescope. The excitement around K2-18b makes much more sense when we remember the incredible instrument behind these findings, the James Webb Space Telescope. Launched on Christmas Day in 2021 after decades of planning, delays, and billions of dollars in investment, Webb was built to be humanity's most powerful eye in space. Unlike the Hubble Space Telescope, which primarily captures images in visible and ultraviolet light, Webb is designed to see in infrared. This is crucial, because infrared light allows us to peer into places we couldn't reach before, through thick clouds of gas and dust, into the early universe, and, most importantly for our story, into the atmospheres of distant worlds orbiting faraway stars. To put it simply, Webb is not just another telescope. It's a leap in technology. Its massive gold-coated mirror, spanning over 6.5 meters, collects more light than any space telescope before it. It orbits at a special point in space called Lagrange Point 2, about 1 million miles from Earth, where it can stay cool and stable, shielded from the sun's heat by its tennis court-sized sunshield. Everything about Webb was built to push the boundaries of what we can observe. One of its primary scientific goals is to study exoplanets. These are planets outside our solar system, orbiting stars many light-years away. Before Webb, astronomers could detect exoplanets, measure their sizes, estimate their distances from their stars, and sometimes infer what they were made of. But Webb brought a whole new level of detail. It can study the light that passes through or reflects off a planet's atmosphere, teasing out the chemical fingerprints of molecules like water vapor, methane, carbon dioxide, and even more complex compounds. For the first time in human history, we can begin to not just know that these worlds exist, but to ask, What are they like? Could they be habitable? This is why the K2-18b story matters so much. Webb was designed for exactly this kind of discovery. Its instruments, particularly its spectrographs, can dissect starlight filtered through a planet's atmosphere and identify what gases are present. And that is where the conversation about life begins. Detecting water vapor suggests liquid oceans might be possible. Detecting methane and carbon dioxide in the right balance could point toward biological activity. Finding unusual molecules like dimethyl sulfide, if confirmed, would be even more tantalizing, because on Earth, that compound comes almost exclusively from living organisms. So when people read that Webb might have found a planet with a 99.7% chance of life, it isn't coming out of nowhere. It's the direct result of Webb's ability to do something humanity has never been able to do before. Look at another planet, orbiting another star, and peer into its skies as if we were standing right there. It is as though we've suddenly developed the ability to breathe in the atmosphere of an alien world and test its chemistry for signs of life. The James Webb Space Telescope is not just humanity's latest gadget. It's our time machine, our interstellar microscope, and our first real attempt to bridge the gap between wondering about alien life and actually finding it. Every observation it makes brings us closer to answering the oldest question we've ever asked. Are we alone? When we talk about K2-18b, or any world beyond our solar system, we're really diving into one of the most transformative discoveries of modern astronomy, the existence of exoplanets. Exoplanets are planets that orbit stars other than our Sun. They were once the stuff of speculation and science fiction, but today we know they are everywhere. The first confirmed detection of an exoplanet orbiting a Sun-like star came in 1995, when astronomers Michel Mayor and Didier Queloz announced they had found a planet around 51 Pegasi, a discovery that won them the Nobel Prize decades later. Since then, the count has exploded. Thanks to missions like Kepler, TESS, and now the James Webb Space Telescope, we've confirmed the existence of thousands of exoplanets, with estimates suggesting that our galaxy alone might hold hundreds of billions of them. Think about that for a second. Every star you see in the night sky, and even the countless ones you can't see with the naked eye, may have their own families of planets, just like our Sun does. Some of those planets are scorched gas giants that whip around their stars in just a few days. Others are icy spheres far from their parent star's warmth. Some are rocky, Earth-sized, and orbit in just the right position where liquid water could exist. This incredible diversity is why the field of exoplanet research has exploded. It's as if we've suddenly discovered a galactic zoo of worlds, each with its own unique story. But why are scientists so obsessed with them? And why do we keep hearing about habitable zones and biosignatures? The answer is tied to one of humanity's oldest questions. Is life unique to Earth, or is it a universal phenomenon? For decades, we had only one data point, Earth. We knew life could thrive here, under the conditions our planet provided. Liquid water, an atmosphere with the right balance of gases, and a steady supply of energy from our Sun. The search for exoplanets has given us thousands of new data points to compare against Earth, helping us identify which conditions might be common and which might be rare. Scientists search exoplanets for signs of habitability because the chemistry of life as we know it depends on certain basics. The most important of these is liquid water. Everywhere on Earth that we find water, whether it's in the boiling pools around deep-sea hydrothermal vents, in frozen Antarctic lakes, or even inside rocks miles underground, we also find life. That's why follow the water has become the guiding principle of astrobiology. If a planet or moon has water in liquid form, there's a chance it could host life. But water alone isn't enough. The atmosphere of a planet also plays a huge role. It not only protects the surface from harmful radiation but also regulates temperature and allows for the complex chemistry that life depends on. By studying exoplanet atmospheres, scientists look for combinations of gases that might indicate biological processes. For example, Earth's atmosphere is rich in oxygen and contains trace amounts of methane. Oxygen is highly reactive, so if it weren't being constantly replenished by life, through photosynthesis, it would vanish over geological timescales. Methane, meanwhile, is produced both biologically and geologically, but the combination of the two gases in the proportions we see on Earth is a strong biosignature. This is why the search for life has shifted so strongly to exoplanets. In our solar system, we've identified a few promising places: Mars, Europa, Enceladus, Titan, where microbial life might exist or might once have existed. But when we look beyond the solar system, the number of possibilities explodes. Imagine the Milky Way as a cosmic ocean, and every star as an island. If just a small fraction of those islands have environments where life can thrive, then the galaxy could be teeming with biology. Detecting life from light years away isn't easy, though. Scientists can't just send a probe to K2-18b. It's over 120 light-years away. Instead, they rely on incredibly subtle measurements of starlight. When a planet passes in front of its star, some of the starlight filters through the planet's atmosphere. Different gases absorb light at specific wavelengths, creating what's known as a spectral fingerprint. By studying these fingerprints, telescopes like Webb can determine what molecules are present. If we detect water vapor, methane, carbon dioxide, or oxygen in the right proportions, it becomes a tantalizing clue. But there's another reason scientists are so focused on exoplanets: perspective. For most of human history, Earth was considered unique, even central to the cosmos. The discovery of exoplanets has shattered that idea. Not only are we not the center of the universe, but we're not even the only planetary system. Planets are the rule, not the exception. This realization reshapes how we think about life. If the conditions that created Earth and life here are common, then perhaps life is common too. If life emerges readily when the conditions are right, then maybe the universe is filled with it. There's also the philosophical and cultural dimension. Searching for exoplanets and studying their atmospheres isn't just about science, it's about wonder. It's about looking up at the night sky and knowing that some of those distant stars have worlds with rainstorms, oceans, winds, and climates of their own. Some of them might even have living creatures swimming in their seas or crawling on their surfaces, unaware that a species on a tiny blue planet across the galaxy is peering into their skies. The exoplanet revolution has essentially opened a new chapter in human exploration. Instead of sending ships across oceans or rockets across space to other worlds in our solar system, we are now stretching our curiosity to entirely different star systems. And with instruments like the James Webb Space Telescope, we're beginning not only to find these worlds but to characterize them. We're asking questions that were once science fiction. What is their weather like? Do they have clouds? Could there be alien biology shaping their atmospheres? All of this builds the foundation for why the discovery of K2-18b is so electrifying. It's not just one more planet added to a growing list. It's a world that sits at the crossroads of all these questions. It orbits in the habitable zone of its star. It may have liquid water. It has intriguing atmospheric chemistry that hints at possible biological activity. In short, it embodies everything exoplanet science has been working toward for decades. And as we continue to unravel the mystery of K2-18b, we're really testing the larger hypothesis behind exoplanet research, that Earth is not unique, and that the story of life may be a universal one written across countless worlds. The story of K2-18b begins not with the James Webb Space Telescope, but with one of Webb's most important predecessors, the Kepler Space Telescope. Launched in 2009, Kepler was designed to do one thing better than any telescope before it: find planets orbiting other stars. It used what's known as the transit method, an ingenious but deceptively simple technique. Kepler would fix its gaze on a patch of the sky and monitor the brightness of thousands upon thousands of stars. If a planet passed in front of one of those stars, even if the planet was too small or too distant to be seen directly, the star's light would dip ever so slightly. These tiny, periodic dips in brightness revealed the presence of planets. For 4 years, Kepler gathered a treasure trove of data. It confirmed thousands of exoplanets and revolutionized our understanding of just how common planets are in the galaxy. But Kepler's story wasn't without obstacles. In 2013, the telescope suffered the failure of 2 of its 4 reaction wheels, critical components that helped it maintain its precise pointing. Many thought Kepler's mission was over. But NASA scientists found a clever way to use the spacecraft's remaining functionality. By balancing against the pressure of sunlight, they could stabilize Kepler enough to continue observing, though not in its original fixed field of view. This became known as the K2 mission, essentially Kepler's second life. It was during this extended K2 phase that K2-18b was discovered. In 2015, using data from this repurposed mission, astronomers identified a star about 120 light-years away in the constellation Leo. This star, later designated K2-18, was dimmer and smaller than our Sun, a type of star known as a red dwarf. Kepler's sensitive instruments picked up the telltale signal of a planet passing in front of it, a small, regular dip in brightness. After careful analysis, scientists confirmed the existence of an exoplanet, which they named K2-18b, following the convention of naming planets after their host star. The discovery was intriguing right from the start. Based on the amount of starlight it blocked and the time it took to complete an orbit, astronomers learned that K2-18b was larger than Earth, somewhere between our planet and Neptune in size. It orbited its red dwarf star every 33 days, placing it in the so-called habitable zone, where temperatures might allow liquid water to exist. That detail alone made K2-18b a prime candidate for further study. Out of the thousands of exoplanets Kepler and other telescopes had found, only a fraction were located in their star's habitable zone. Even fewer were of a size and composition that suggested they might have conditions suitable for life. K2-18b checked enough of those boxes to move into the spotlight. The initial discovery was exciting, but it also raised more questions than it answered. Was K2-18b a rocky super-Earth with a thick atmosphere? Was it more like a mini-Neptune, with a puffy gaseous envelope and no solid surface? Could it have oceans beneath its atmosphere? These were mysteries Kepler itself couldn't resolve. It was designed to find planets, not study their atmospheres in detail. But the identification of K2-18b meant that future telescopes, more advanced and more specialized, could target it for follow-up observations. And that's exactly what happened. The Hubble Space Telescope, still operational at the time, was tasked with observing K2-18b. In 2019, Hubble detected evidence of water vapor in its atmosphere, sparking worldwide headlines. This was the first time scientists had identified water in the atmosphere of an exoplanet in the habitable zone. Suddenly, K2-18b was no longer just another exoplanet. It was a genuine candidate for habitability. The stage was set for Webb, with its far superior infrared instruments, to take the baton and push the investigation much further. So while the headlines today focus on the James Webb Space Telescope's extraordinary findings, it's important to remember that the story of K2-18b began with Kepler's quiet persistence. Even after a partial mechanical failure, Kepler's second life in the K2 mission was enough to reveal one of the most intriguing planets in our search for life. It's a reminder of how scientific discovery is often a relay race. One mission identifies a target. Another builds on it. Each step carries the story forward until, eventually, we find ourselves on the brink of answering questions once thought impossible. When scientists first pieced together the basic physical characteristics of K2-18b, they quickly realized it didn't fall neatly into any of the categories we were most familiar with. It wasn't a rocky, Earth-sized world. It wasn't a gas giant like Jupiter or Saturn. And it wasn't even a full Neptune-sized planet. Instead, it landed in a class that astronomers often call sub-Neptunes or mini-Neptunes, planets larger than Earth but smaller than Neptune, with properties that remain one of the most puzzling frontiers in planetary science. K2-18b is estimated to be about 2.6 times the radius of Earth. That makes it considerably larger than our planet, but nowhere near as huge as Neptune, which is nearly 4 times Earth's radius. Its mass is calculated to be roughly 8.6 times that of Earth. With those two numbers, radius and mass, we can determine its density, and that density provides clues to its composition. The numbers suggest that K2-18b is too light to be a purely rocky planet like Earth, but also too dense to be a puffy gas giant. That's why scientists categorize it as a sub-Neptune. It likely has a significant hydrogen-rich atmosphere surrounding either a rocky or icy core. In terms of orbit, K2-18b circles its host star once every 33 Earth days. Now, that might sound alarmingly close. After all, Earth takes 365 days to orbit the Sun. But the key detail is that K2-18's host star is a red dwarf, which is smaller and cooler than our Sun. Because the star puts out less energy, a planet can orbit much closer to it while still receiving an amount of radiation comparable to what Earth receives from the Sun. K2-18b's orbit places it squarely in what astronomers call the habitable zone, the region around a star where temperatures could, at least in theory, allow liquid water to exist on a planet's surface. From Earth, K2-18b is located about 120 light-years away in the constellation Leo. That's relatively close on cosmic scales, practically our interstellar neighborhood, but still unimaginably distant in human terms. If we could somehow travel at the speed of light, it would take 120 years to get there. At current spacecraft speeds, it would take millions of years. That's why direct exploration is impossible for now, and why telescopes like Webb are our only window into these alien worlds. The planet's classification as a sub-Neptune makes it especially intriguing. In our solar system, there are no sub-Neptunes. We have terrestrial planets like Mercury, Venus, Earth, and Mars. We have ice and gas giants like Neptune, Uranus, Saturn, and Jupiter. But nothing in between. This gap makes planets like K2-18b both mysterious and invaluable, because they represent types of worlds that might actually be the most common in the galaxy. What does a sub-Neptune look like? That's harder to answer. Some models suggest these planets could be enveloped in thick, hydrogen-dominated atmospheres, with crushing pressures below the cloud tops. Others suggest they might hide vast global oceans beneath those atmospheres, making them water worlds unlike anything we've seen locally. K2-18b sits right in the middle of this debate. Its size and mass mean it likely has a thick atmosphere, but whether there's a rocky surface beneath it, or a deep ocean layer, is still up for debate. Another fascinating aspect of K2-18b's orbit is its stability. Red dwarf stars are known for being active, often flaring with bursts of radiation that could strip a planet's atmosphere or make it hostile to life. Yet K2-18b seems to have maintained its atmosphere, which tells us something important about its resilience. Despite being so close to its star, it hasn't been blasted into a barren rock. That alone is a promising sign, because it means the planet has likely retained conditions favorable for chemistry and maybe even biology. When you put all these facts together, the size, the mass, the orbit, the classification as a sub-Neptune, you start to see why K2-18b is such a compelling target. It doesn't fit neatly into the categories of planets we know from our solar system, but it exists in a region of space where liquid water could theoretically persist. It's large enough to have held onto a thick atmosphere for billions of years, and its orbit around a relatively cool red dwarf means it could be bathed in just the right amount of starlight. The mystery deepens when we imagine what the surface, or perhaps the ocean, of K2-18b might be like. If it has a solid or liquid layer beneath its thick atmosphere, it could potentially host conditions that are life-friendly, even if they're very different from Earth's. And if it's mostly a gaseous envelope with no solid surface, the chemistry within its clouds could still support microbial forms of life, much like some scientists speculate might be possible in the upper atmosphere of Venus. In other words, the basic facts of K2-18b don't just describe a planet, they open the door to entirely new categories of habitability. The planet challenges our definitions of what a habitable world can be. Earth is not the blueprint for all life-bearing planets. Instead, planets like K2-18b force us to expand our imaginations and reconsider where life might thrive. To truly understand K2-18b, we also need to look at the star it calls home, because a planet's host star determines so much about its climate, its atmosphere, and its long-term stability. K2-18b orbits a star known simply as K2-18, which is classified as a red dwarf, or more technically, an M-dwarf star. These are the smallest, coolest, and most common stars in the galaxy. In fact, red dwarfs make up about 70 to 75% of all stars in the Milky Way, which means if you go out looking for planets, odds are high you'll end up finding them around stars like K2-18. Red dwarfs are significantly smaller and dimmer than our Sun. K2-18 itself is thought to be only about 40% the mass of the Sun and less than half its radius. Because of this, it emits much less energy. To put it into perspective, if Earth orbited a star like K2-18 at the same distance it orbits the Sun, it would be a frozen wasteland. But because K2-18 is dimmer, its habitable zone, the region where liquid water could exist, is much closer in. That's why K2-18b can orbit its star every 33 days and still receive a level of energy comparable to what Earth gets in a year from the Sun. Now, here's where things get interesting. On the one hand, red dwarfs are fantastic targets in the search for exoplanets. Because they're smaller and dimmer, it's easier to detect the subtle dimming when a planet passes in front of them. This makes the transit method, used by Kepler and now studied in detail by Webb, especially effective. It also means that planets in the habitable zone of red dwarfs orbit close enough that they transit frequently, giving astronomers many opportunities to observe them. From a detection standpoint, red dwarfs are almost tailor-made for finding habitable zone exoplanets. But on the other hand, red dwarfs come with challenges. They are known to be highly active stars, especially in their youth. They can unleash massive flares and bursts of ultraviolet and X-ray radiation that would be devastating to a nearby planet's atmosphere. These flares could strip away protective gases, leaving the planet exposed to harsh radiation. In some cases, they could sterilize the surface entirely. This has led to a lively debate in the scientific community. Are red dwarfs nurturing stars that quietly host billions of life-friendly planets, or are they hostile furnaces that fry any world unlucky enough to orbit them closely? In the case of K2-18b, the answer isn't fully clear yet. The fact that the planet still seems to have a substantial atmosphere is encouraging. It means the planet has likely managed to hang on to its gases despite any stellar activity. That resilience makes it even more intriguing as a candidate for habitability. It suggests that, under the right conditions, life might be able to adapt or endure even in the unpredictable environments around red dwarfs. K2-18, the star itself, lies in the constellation Leo, about 120 light-years from Earth. To the human eye, even with a good telescope, it's not much to look at, a faint red point of light that blends into the background of the night sky. But appearances can be deceiving. For astronomers, it's a treasure. Its relative proximity makes it a prime target for detailed observation. Webb, with its extraordinary sensitivity, can study the starlight passing through K2-18b's atmosphere in exquisite detail precisely because the system is not too far away. At 120 light-years, it's far beyond anything humanity could visit with spacecraft in the foreseeable future, but close enough that our telescopes can still gather meaningful data. Another factor worth considering is the long lifespans of red dwarfs. While stars like our Sun burn steadily for about 10 billion years before evolving into red giants, red dwarfs can burn for trillions of years. Their nuclear fusion runs at such a slow pace that they're essentially eternal compared to other stars. This means any planets orbiting them could have stable conditions for incredibly long stretches of cosmic time, much longer than Earth will have around our Sun. If life managed to take hold on a planet like K2-18b, it could have billions or even trillions of years to evolve, adapt, and flourish. From the standpoint of habitability, that's a massive advantage. However, there's one more wrinkle. Because K2-18b is so close to its star, it's very likely tidally locked. This means one side of the planet always faces the star in perpetual daylight, while the other side is in eternal darkness. On Earth, we experience day and night because we rotate relative to the Sun, but for K2-18b, that rotation might be locked into synchronization with its orbit. Tidal locking can create extreme temperature differences, scorching heat on the day side and freezing cold on the night side. But it can also create a twilight zone along the terminator line, the thin band between light and dark, where conditions might be just right for life. And if the atmosphere is thick enough, it could distribute heat around the planet, softening these extremes. So, when we talk about K2-18b's host star, we're talking about both a challenge and an opportunity. Red dwarfs like K2-18 are abundant and long-lived, making them natural laboratories for the search for life. But they also come with violent personalities that could strip or scorch a planet's surface. Whether K2-18b is a victim of its star's activity or a survivor thriving under its dim, steady glow is exactly the kind of question Webb was built to answer. From our vantage point on Earth, K2-18 and its planet don't seem like much. A faint star, too dim to see without instruments, and a planet far too distant to visit. But in that faint red light lies the potential answer to one of the greatest mysteries we've ever asked. Are we alone? When astronomers talk about planets like K2-18b, one term comes up again and again, the habitable zone. It's sometimes called the Goldilocks zone, because it refers to the region around a star that is not too hot, not too cold, but just right for liquid water to exist on a planet's surface. And liquid water, at least as far as we know, is the single most important ingredient for life. The concept is straightforward in theory. If a planet orbits too close to its star, the heat will boil away any water, leaving behind a scorched, desert-like world. This is what we see with Venus in our solar system, which lies near the inner edge of the Sun's habitable zone but is unlivable due to extreme greenhouse heating. If a planet orbits too far away, the star's light is too weak, and water freezes into ice. Mars, for example, is near the outer edge of the Sun's habitable zone and today is a frozen desert with only traces of liquid water under specific conditions. In between lies the habitable zone, that sweet spot where the temperature could allow oceans, lakes, and rivers of liquid water. For our Sun, Earth sits squarely in the middle of this region, which is one reason life has flourished here. But the exact distance of the habitable zone depends on the star. A massive, hot star will have a habitable zone that is very far out, while a smaller, cooler star like a red dwarf will have a habitable zone that hugs closely around it. K2-18b orbits its host star at just the right distance, close enough to stay warm, but not so close that it's doomed to a Venus-like runaway greenhouse effect. Even though it completes an orbit in only 33 days, its star, K2-18, is a dim red dwarf that shines with only a fraction of the Sun's energy output. For comparison, Mercury whips around our Sun in 88 days and is blasted by solar radiation, making it far too hot for life. But because K2-18 is much cooler, K2-18b can orbit much closer while still receiving a similar amount of energy to what Earth gets from the Sun. This delicate balance places it firmly in its star's habitable zone. It's important to note that being in the habitable zone doesn't guarantee habitability, it only makes it possible. The zone defines where liquid water could exist, but whether it actually does depends on many other factors: the planet's atmosphere, its composition, its history, and its star's behavior. For example, a planet in the habitable zone with no atmosphere would be a lifeless rock, while another with a runaway greenhouse atmosphere could be suffocatingly hot. So the habitable zone is really just the starting line in the race to identify potentially life-friendly planets. What makes K2-18b especially interesting is that its size and mass suggest it's not a rocky Earth twin but rather a sub-Neptune. That means it might not have a solid surface where liquid water could pool like Earth's oceans. Instead, scientists think it could be what's called a Hycean world, a planet with a thick hydrogen atmosphere surrounding a deep global ocean. In such a scenario, the habitable zone definition becomes more flexible. Even if conditions at the surface are unlike Earth's, a deep ocean beneath the atmosphere could still be warm enough to remain liquid, providing a potentially stable environment for life. Another wrinkle comes from the fact that K2-18 is a red dwarf. Red dwarfs have habitable zones much closer in, but they're also prone to stellar flares, as mentioned earlier. These bursts of radiation can strip atmospheres or bombard planets with energy that makes life harder to sustain. The good news is that K2-18b appears to have maintained an atmosphere despite this potential hazard, meaning its position in the habitable zone might truly matter. The discovery of water vapor in its atmosphere by the Hubble Space Telescope back in 2019 was a key piece of evidence here. If there's water vapor in the air, it strengthens the argument that water in liquid form could exist below. And with Webb's more detailed observations now detecting methane and carbon dioxide, the case for habitability becomes even more compelling. When you put all of this together, K2-18b emerges as one of the most intriguing candidates we've ever found. It sits in the habitable zone of its star, it has signs of water vapor, it maintains a substantial atmosphere, and its chemistry hints at potential biosignatures. In short, it checks more boxes than most exoplanets we've discovered so far. The habitable zone concept is powerful because it gives us a way to filter through the thousands of exoplanets astronomers find. Not every planet is worth closer study. Hot Jupiters scorched by their stars aren't going to host life as we know it. Frozen gas giants on the edges of their systems are equally unlikely. But a planet like K2-18b, sitting comfortably in the Goldilocks zone of a relatively nearby star, is irresistible. It's exactly the kind of world the James Webb Space Telescope was designed to investigate. And here's the bigger picture. If K2-18b, a sub-Neptune in a red dwarf system, turns out to host conditions favorable for life, it could completely reshape how we define habitability. It would mean that life doesn't just require an Earth-like planet around a Sun-like star. It could thrive under very different circumstances, in environments that once seemed alien and hostile. It would expand the habitable zone concept itself, making the galaxy look far more fertile than we once imagined. So when scientists say K2-18b lies in the habitable zone, it's not just a technical classification. It's a beacon of possibility, a hint that somewhere under that hydrogen sky, in that dimly lit system 120 light-years away, there could be oceans, chemistry, and perhaps even biology. When the James Webb Space Telescope turned its golden mirror toward K2-18b, it wasn't just another telescope looking at another planet. It was the beginning of a new era in how we study alien worlds. For decades, astronomers could only dream of directly probing the atmospheres of planets orbiting distant stars. We could detect them, estimate their sizes, even guess at their compositions, but actually analyzing their skies for signs of water, methane, carbon dioxide, or other life-related molecules, that was beyond our reach. Webb changed that. At the heart of Webb's ability lies its unmatched sensitivity to infrared light. Infrared is key because many of the most important molecules for life leave their chemical fingerprints in this part of the spectrum. When starlight passes through a planet's atmosphere during a transit, that moment when the planet crosses in front of its star, molecules in the atmosphere absorb certain wavelengths of that light. This creates tiny dips, like barcodes, in the spectrum of the starlight. By carefully analyzing those dips, scientists can identify what molecules are present in the atmosphere. Earlier telescopes, like Hubble, could attempt this kind of spectroscopy, but their instruments were limited. Hubble, for instance, could detect water vapor in some atmospheres, and in 2019 it did exactly that for K2-18b. But it couldn't see the full chemical picture. Webb, with its near-infrared spectrograph, NIR-SPEC, and near-infrared imager and slitless spectrograph, NIRIS, takes this to an entirely new level. These instruments don't just detect water, they can resolve a rich spectrum that includes carbon-bearing molecules, methane, carbon dioxide, and potentially even rarer compounds that might indicate biological processes. Another advantage Webb brings is its sheer size. Its primary mirror is 6.5 meters across, far larger than Hubble's 2.4 meters. The larger the mirror, the more light it collects, and the fainter the signals it can detect. For a planet like K2-18b, orbiting a dim star 120 light-years away, that difference is everything. The amount of light passing through the planet's atmosphere and reaching us is minuscule, but Webb's enormous mirror is sensitive enough to capture it. Then there's Webb's location. It doesn't orbit Earth the way Hubble does. Instead, it sits at the second Lagrange point, L2, about 1 million miles from Earth. This stable vantage point allows Webb to keep its instruments cold and shielded from sunlight with its massive sun shield. For infrared astronomy, cold is critical. Any heat from the telescope itself would interfere with the delicate infrared signals it's trying to detect. At L2, Webb is perfectly positioned to carry out long, uninterrupted observations of exoplanets like K2-18b without Earth constantly moving in and out of the way. Webb's role isn't just technical, it's also transformative in how we approach the search for life. Before Webb, the study of exoplanet atmospheres was limited to a handful of cases with incomplete data. With Webb, suddenly we can build detailed atmospheric profiles, not just for one planet but for many. K2-18b is one of the first, but it won't be the last. Webb is opening the door to cataloging the chemistry of dozens, even hundreds, of exoplanets. Some will be barren. Some will surprise us. And some, like K2-18b, may show tantalizing hints that life could exist. What Webb revealed about K2-18b is exactly why it was built. It confirmed the earlier hints of water vapor, but it went further, detecting methane and carbon dioxide, while noting the absence of ammonia. These details matter because they don't just tell us what's in the atmosphere, they tell us about the planet's overall environment. The balance of gases suggests that K2-18b could be a Hycean world, with a hydrogen-rich atmosphere and possibly a global ocean beneath it. Without Webb, we wouldn't have this level of clarity. And Webb is just getting started. Its instruments can perform repeated observations of K2-18b and other targets, refining the data and teasing out even fainter molecular signatures. The possible detection of dimethyl sulfide, DMS, a molecule almost exclusively produced by life on Earth, came from Webb's extraordinary sensitivity. That detection is still tentative, but the fact that it's even on the table shows how far Webb has pushed the frontier. It's worth emphasizing how astonishing this capability is. Think about it. We are looking at a planet 120 light-years away, separated from us by unimaginable distances. We can't send a probe there. We can't even see the planet directly with our eyes. And yet, with Webb's instruments, we can tell what gases are floating in its skies. It's like standing on a mountaintop on Earth and being able to tell, by looking at a faint star, whether a planet orbiting it has water clouds, methane, or oxygen. That is the scale of the breakthrough Webb represents. In many ways, Webb has become the ultimate detective in our cosmic search. It doesn't just find planets, it interrogates them. It asks, what's in your atmosphere? Do you have water? Do you have the gases that life produces? Are you hiding oceans beneath your clouds? And in the case of K2-18b, the answers it's finding are among the most exciting we've ever received. This is why the claim of a 99.7% chance of life on K2-18b resonates so strongly. It isn't random speculation, it comes from the unprecedented detail Webb is giving us. Whether that claim ultimately holds true or not, the fact that we can even approach the question with data this precise is revolutionary. Webb has transformed the search for life from philosophy and theory into something measurable, testable, and scientific. And K2-18b is just the beginning. As Webb continues its mission, we'll be hearing about many more worlds. Some may be disappointing. Others may be breathtaking. But every spectrum it records, every atmospheric fingerprint it captures, brings us closer to answering the question that has haunted humanity for millennia. Are we alone in the universe, or are there others out there, waiting to be discovered? One of the most remarkable abilities of the James Webb Space Telescope is its power to read the atmospheres of planets orbiting distant stars, a feat that seems almost impossible when you consider the distances involved. K2-18b is 120 light-years away. That's about 1.1 quadrillion kilometers, or nearly 700 trillion miles. And yet, from this unimaginable distance, Webb can tell us what molecules are drifting in its skies. The way it does this comes down to one of the most powerful tools in astronomy: spectroscopy. To understand spectroscopy, imagine white light passing through a prism. The light spreads out into a rainbow of colors: red, orange, yellow, green, blue, indigo, violet. That rainbow is a spectrum. Now imagine that certain colors are missing, leaving behind thin dark lines. Those missing lines are where specific atoms or molecules have absorbed light at very precise wavelengths. Each element and each molecule has its own unique pattern of absorption lines, like a fingerprint. This is the foundation of spectroscopy. By looking at how light is absorbed, scientists can identify what substances are present. When it comes to exoplanets, the trick is to catch starlight as it interacts with a planet's atmosphere. There are a few ways Webb does this, but the most important one is during a transit, the moment when the planet crosses in front of its star from our point of view. As the planet passes, some of the star's light filters through the thin layer of atmosphere around the planet before it reaches us. That atmosphere imprints its chemical fingerprints onto the starlight. Webb collects that light, spreads it into a spectrum, and analyzes it to see which wavelengths are absorbed. From those absorption features, astronomers can deduce what molecules are present in the planet's atmosphere. For K2-18b, Webb's instruments, especially the near-infrared spectrograph (NIR spec) and the near-infrared imager and slitless spectrograph (NIRIS), were crucial. They work in the infrared, which is ideal because molecules like water vapor, methane, and carbon dioxide all have strong signatures in that part of the spectrum. When Webb pointed at K2-18b during its transit, it captured incredibly precise data on how the starlight dimmed and shifted across different wavelengths. That subtle dimming, invisible to the naked eye, contains the molecular fingerprints. It's worth emphasizing how subtle these signals are. K2-18b's atmosphere is not glowing for us to see directly. Instead, we're detecting the faintest changes in starlight, sometimes less than a fraction of a percent of the total light. Imagine standing miles away from a lighthouse and trying to tell what kind of fog is drifting in front of it, just by looking at tiny color changes in its beam. That's the scale of what Webb is doing, but with far greater precision. There are also other methods besides transit spectroscopy. For example, when a planet passes behind its star in what's called a secondary eclipse, Webb can measure the difference in light before and after the eclipse. This tells us how much light is coming from the planet itself, usually as infrared radiation. From that, scientists can infer the temperature and composition of the planet's atmosphere. Over time, Repeated observations like this can even hint at weather patterns, cloud structures, and climate dynamics on distant worlds. In K2-18b's case, Webb's data revealed a spectrum with absorption features pointing to water vapor, methane, and carbon dioxide, while showing a lack of ammonia. Each of these results came directly from spectroscopy. Water vapor leaves strong absorption features in infrared light. Methane absorbs at different, equally distinct wavelengths. By matching the dips in the spectrum with the known fingerprints of these molecules, scientists can say with confidence that they exist in K2-18b's atmosphere. This ability to decode alien atmospheres is what makes Webb such a game-changer. Before, exoplanets were mostly dots of data, a radius here, a mass there, an orbit calculated from transit timing. Now, thanks to spectroscopy, they are worlds with skies, clouds, and chemistry we can study in detail. We've moved from knowing exoplanets exist to beginning to understand what it might be like to stand beneath their atmospheres, what gases you'd breathe or choke on, what kind of weather you'd experience, and whether those conditions could sustain life. Spectroscopy also gives us a way to search for biosignatures, the chemical clues that life might be present. On Earth, life alters our atmosphere in measurable ways. Plants release oxygen, microbes produce methane, and the combination of gases like oxygen and methane in the same atmosphere is difficult to explain without biology. If Webb, or future telescopes, find similar patterns in exoplanet spectra, it could be the first real evidence of life beyond Earth. For K2-18b, Webb spectroscopy hasn't just revealed molecules, it's hinted at possibilities that stretch the imagination. The tentative detection of dimethyl sulfide, DMS, a molecule on Earth produced almost entirely by life, came from spectroscopy. That result is still uncertain and needs more data, but even the possibility shows just how powerful this method is. Think about the bigger picture. With nothing more than light, captured from over 100 trillion miles away, Webb can read the chemical makeup of a planet's atmosphere. It's like being able to identify the contents of a perfume bottle sitting on a table in another city, just by analyzing the way a street lamp's light shines through it. It sounds impossible, and yet it's exactly what spectroscopy allows us to do. This is why Webb is at the center of the excitement around K2-18b. Without spectroscopy, we wouldn't know there's water vapor. We wouldn't know about the methane and carbon dioxide. We wouldn't know that ammonia seems absent. And we wouldn't even be talking about the possibility of biosignatures. All of that knowledge flows directly from the power of Webb's instruments to dissect starlight with unparalleled precision. When scientists first pointed their instruments toward K2-18b, one of the earliest and most tantalizing discoveries was the presence of water vapor in its atmosphere. This finding is not just a minor detail, it's the reason this planet shot to fame in the scientific community and became a prime candidate for James Webb's deeper investigations. Water, after all, is the molecule most closely tied to our understanding of life. Wherever we find it on Earth, whether in the oceans, locked in ice, or hidden in underground aquifers, we find life clinging to it. So when astronomers detected water vapor around a planet orbiting another star, the implications were enormous. The first hints came in 2019, when the Hubble Space Telescope trained its instruments on K2-18b. Even though Hubble is less powerful than Webb, it was able to perform a kind of transit spectroscopy, analyzing how starlight passed through the planet's atmosphere during its orbit. In the faint fingerprints of the light spectrum, Hubble saw something remarkable: signs of water vapor. This was the very first time water vapor had ever been definitively detected in the atmosphere of a planet lying within the habitable zone of its star. It was a historic milestone, a moment when the search for life moved from theory to evidence-based discovery. But Hubble's data, while groundbreaking, was limited. It could confirm that water vapor existed, but it couldn't tell us how much was present, how it was distributed in the atmosphere, or whether the planet truly had conditions that could sustain oceans. That's where Webb entered the picture. Equipped with its next-generation infrared spectrographs, Webb revisited K2-18b with far greater precision. Its instruments could probe deeper into the infrared spectrum, where water vapor leaves its strongest fingerprints. And what Webb confirmed was even more compelling. The presence of water vapor was real, and it seemed to be a consistent feature of K2-18b's atmosphere. This matters because water vapor is more than just a chemical curiosity. It's a tracer, a signpost pointing to deeper possibilities. If there's water vapor in the air, It raises the possibility that liquid water exists below, perhaps in vast oceans hidden beneath the thick hydrogen-rich atmosphere that K2-18b appears to possess. And since liquid water is considered a universal requirement for life as we know it, this makes K2-18b a uniquely intriguing world. It's also worth noting the rarity of such a detection. Scientists have catalogued thousands of exoplanets, but very few have revealed clear atmospheric features. Most are either too small, too faint, or too close to their stars for us to analyze their atmospheres in detail. To find water vapor on a planet not only in the right kind of orbit but also with an atmosphere we can probe is like finding a needle in a galactic haystack. Out of all the known exoplanets, K2-18b stands out as one of the most promising candidates for habitability, and water vapor is the reason why. Another layer of intrigue comes from the fact that K2-18b is not an Earth twin. It's a sub-Neptune, a class of planet larger than Earth but smaller than Neptune, with no direct counterpart in our solar system. Scientists used to assume that such planets were unlikely places to search for life. They were thought to be too gaseous, with thick atmospheres crushing any chance of Earth-like conditions. But the detection of water vapor challenges that assumption. It suggests that even planets very different from Earth might harbor the conditions necessary for life. In other words, water vapor on K2-18b expands the definition of what habitable might mean. Webb's water vapor findings also fit into a bigger picture. When combined with its detection of methane and carbon dioxide, and the absence of ammonia, the evidence paints a picture of a planet that could have a Hycean environment, a hydrogen-rich atmosphere above a deep, global ocean. In this model, water vapor in the atmosphere isn't just an isolated feature. It's part of a stable water cycle, with evaporation, condensation, and potentially even cloud formation. That makes the detection of water vapor not just exciting, but crucial for building a case that this planet could host life-supporting conditions. And we shouldn't underestimate the emotional impact of this finding. For centuries, water has symbolized life and hope in human culture. Ancient civilizations built their settlements around rivers and seas. Explorers searching Earth always sought water sources first. And now, in the 21st century, our most advanced space telescope is doing the same thing on a cosmic scale. The discovery of water vapor on K2-18b resonates deeply because it connects our age-old instincts with modern science. If you want to find life, follow the water. What makes this even more astonishing is the scale. We're talking about a planet orbiting a dim red dwarf 120 light-years away. It's not visible to the naked eye. We'll never send spacecraft there in our lifetimes. And yet, through the faintest traces of starlight, we've detected something as fragile and vital as water vapor. It's like standing on one side of a vast ocean and smelling a single drop of perfume spilled on the shore of the opposite side. That's how precise and sensitive Webb's instruments are, and that's why the discovery of water vapor is so groundbreaking. Of course, scientists remain cautious. Detecting water vapor doesn't mean K2-18b is an ocean paradise. The water could exist high in the atmosphere, with crushing pressures and hostile conditions below. The presence of water alone doesn't guarantee habitability. But as part of a broader pattern, including methane, carbon dioxide, and the intriguing possibility of dimethyl sulfide, it makes K2-18b a world we simply cannot ignore. Water vapor is the first piece of the puzzle, the gateway that draws us in. Without it, K2-18b might just be another gas-shrouded planet. With it, the door opens to oceans, chemistry, and maybe even biology. It's the spark that transformed K2-18b from just another name in the exoplanet catalogue into one of the most exciting candidates in the search for life beyond Earth. When the James Webb Space Telescope turned its golden mirror toward K2-18b, scientists were hoping to confirm the water vapor that Hubble had hinted at years before. But Webb went far beyond that expectation. In the spectra it returned, researchers noticed something that added entirely new weight to the conversation about this distant world: methane and carbon dioxide. These two gases may not sound glamorous at first, but their presence in K2-18b's atmosphere is one of the most compelling reasons scientists are whispering the words possible biosignature when they talk about this planet. Let's start with methane. On Earth, methane is a gas we're all familiar with. It's produced naturally by volcanic activity, by chemical reactions deep underground, and, most importantly, by life. Microbes known as methanogens thrive in oxygen-free environments and produce methane as a byproduct of their metabolism. Rice paddies, wetlands, and even the digestive systems of cows are all major sources of methane on our planet. Now, methane can absolutely exist without life. Saturn's moon Titan has methane lakes and an atmosphere rich in hydrocarbons, all generated through chemistry. But here's the critical point. When methane exists alongside other gases like carbon dioxide in the right balance, it becomes harder to explain through non-biological processes alone. That's why Webb's detection was so exciting. In K2-18b's atmosphere, methane wasn't floating in isolation. It appeared in tandem with carbon dioxide, another gas central to the chemistry of habitability. Carbon dioxide plays a massive role on Earth. It regulates climate, helps trap heat in the atmosphere, and cycles through the biosphere via plants, oceans, and volcanic activity. Its presence on K2-18b suggests not only complex atmospheric chemistry, but also the possibility of a stable greenhouse effect that could keep the planet's potential oceans warm enough to remain liquid. Now here's where the story becomes especially intriguing. The methane and carbon dioxide were detected alongside the absence of ammonia. This matters because in many chemical models of sub-Neptune planets with hydrogen-rich atmospheres, you'd expect to see ammonia. Its absence suggests that something unusual is happening in K2-18b's skies, possibly making the environment more favorable for life. Combined with the methane and carbon dioxide, this atmospheric mix begins to resemble conditions that scientists would call life-friendly. Let's pause to consider the bigger implication here. Detecting methane and carbon dioxide together is what scientists often describe as a red flag for life, not a smoking gun, but a very intriguing signal. On Earth, methane doesn't last long in the atmosphere. It gets broken down by sunlight in a matter of decades. That means if you detect it in significant amounts, something must be replenishing it. If that something is life, then methane becomes a powerful biosignature. Add carbon dioxide into the mix, and you have a balance that strongly suggests an active carbon cycle. While volcanic or geological processes could, in theory, produce this balance, it's not the most straightforward explanation. Life, at least on Earth, is the simplest way to sustain it. What makes Webb's finding revolutionary is not just the detection itself, but the precision of the data. Before Webb, we could only speculate about the atmospheric chemistry of distant exoplanets. Now, we're looking at actual fingerprints of gases in real time, dissecting the composition of a world that's more than 100 light-years away. It's almost science fiction made real, using light alone to peer into alien skies and find molecules that hint at life's universal chemistry. Of course, methane and carbon dioxide don't automatically equal biology. Scientists are extremely cautious here, because there are non-biological ways to produce both gases. For instance, methane can form from reactions between water and certain types of rock, a process known as serpentinization. Carbon dioxide can build up from volcanic outgassing. Put those processes together, and you can create atmospheres rich in methane and CO without needing life. That's why the scientific community insists on corroborating evidence. Other molecules, unusual balances, or patterns that can't be explained by geology alone. This is where K2-18b becomes so fascinating. It's not just the presence of methane and carbon dioxide that excites researchers, it's the broader context. This planet sits in its star's habitable zone. It already shows signs of water vapor, and it may even hint at dimethyl sulfide, a molecule almost exclusively produced by life on Earth. When methane and CO are placed in that context, they don't look like ordinary gases. They look like part of a puzzle, and when you start fitting the pieces together, the picture that emerges is profoundly suggestive of habitability. Imagine the implications if this detection holds up under further scrutiny. It would mean that we've not only found a planet in the right orbit but also detected the actual gases that life on Earth depends on. It would be the closest humanity has ever come to sniffing out the breath of an alien biosphere. Just think about it. 120 light-years away, there may be methane bubbling up from microbial colonies in deep oceans, carbon dioxide cycling through a watery atmosphere, and clouds forming in a water cycle not so different from our own. And yet, we must be careful. Webb's instruments are powerful, but this is the first time we've had data of this kind for a planet like K2-18b. Scientists will need multiple follow-up observations to confirm that these signals are real, consistent, and not artifacts of noise or data processing. Already, teams around the world are lining up to reanalyze the spectra, run new models, and test alternative explanations. That's the beauty of science. It's cautious, self-correcting, and unwilling to jump to conclusions until the evidence is overwhelming. Still, methane and carbon dioxide on K2-18b are a big deal. They transform this planet from a curiosity into a front-runner in the search for life. They take us from this might be an interesting sub-Neptune to this might be the first place we found beyond Earth that has the right chemistry for biology. And perhaps most importantly, they prove that Webb can deliver on its promise. Not only to look at distant worlds, but to read their skies, molecule by molecule, and bring us closer to answering the most profound question humanity has ever asked. One of the most overlooked but fascinating aspects of K2-18b's atmospheric profile is not what Webb detected, but what it didn't detect. Amid the signals of water vapor, methane, and carbon dioxide, there was something conspicuously absent: ammonia. To the casual listener, that might sound trivial, just another chemical that happens to be missing. But in the field of astrobiology, the absence of ammonia on K2-18b could be just as important as the presence of other gases, and it may even tilt the scales toward a more life-friendly interpretation of this distant world. Here's why it matters. In many theoretical models of sub-Neptune-type planets, which K2-18b is thought to be, scientists expect significant amounts of ammonia in the atmosphere. Ammonia forms naturally in hydrogen-rich environments, especially under high pressures and cold conditions. If K2-18b was simply a mini-gas giant with a thick, inert envelope of hydrogen and helium, ammonia should be abundant and easy to detect in the spectral data. Its absence, therefore, suggests that something unusual is happening in K2-18b's atmosphere, something that doesn't quite match the standard expectations for a planet of its size and class. The lack of ammonia hints that K2-18b's atmosphere might not be as overwhelmingly hydrogen-dominated as once thought. Instead, it may be more chemically balanced, with a mix of gases that leans toward habitability. Why? Because ammonia in large quantities is actually corrosive and hostile to many forms of life as we know it. It can make environments chemically unstable for the complex organic molecules that biology depends on. So, a world where ammonia is suppressed or absent could be one where chemistry has evolved in a more life-friendly direction. Now, consider how this ties in with the Hycean world hypothesis. Hycean planets are a proposed class of exoplanets with hydrogen-rich atmospheres and deep global oceans. In those models, high levels of methane and carbon dioxide, paired with little to no ammonia, are precisely the kind of atmospheric mix scientists expect if the planet has a stable, water-rich environment beneath its skies. The absence of ammonia on K2-18b strengthens the case that this world could indeed be Hycean, a planet not just with an atmosphere, but potentially with vast oceans capable of supporting biology. From a chemical standpoint, the missing ammonia could point to active processes within the planet's atmosphere or surface. Perhaps ammonia is being destroyed by photochemistry, broken apart by the star's radiation. Or perhaps it's being absorbed into an ocean or reacting with other compounds in ways we don't yet understand. Whatever the mechanism, the fact remains: K2-18b doesn't show the ammonia levels that would be expected from a sterile, purely chemical world. Instead, it shows a cleaner, more balanced chemistry, one that, when combined with water vapor, methane, and carbon dioxide, looks surprisingly Earth-like in its implications. And there's another angle to this. On Earth, ammonia is used in agriculture, refrigeration, and industry. But it's also a compound that biology interacts with constantly. Many microorganisms consume or produce nitrogen-based molecules as part of their metabolism. So when astronomers expected to see ammonia in K2-18b's skies but didn't, it raised the possibility that nitrogen may be locked up in other chemical forms more favorable for life. Perhaps the nitrogen cycle on this planet is more complex than we thought, potentially resembling, in some distant way, the nitrogen cycle that helps sustain ecosystems on Earth. It's important to emphasize that absence doesn't always mean what we want it to. The lack of ammonia could have explanations that don't involve life or habitability. It could be the result of specific formation conditions in the K2-18 system. It could mean the planet lost ammonia over time through processes unrelated to biology. Or it could simply be that the levels are so low they fall beneath Webb's detection limits. But even with those caveats, the result is still powerful, because it pushes K2-18b into a different category of worlds than we previously imagined. It's no longer just another sub-Neptune. It's a world that defies expectations. The absence of ammonia, therefore, becomes part of the larger puzzle. Water vapor suggests oceans. Methane and carbon dioxide suggest active, possibly even biological, chemistry. The lack of ammonia removes one of the chemical obstacles that might have made the environment hostile to life. Taken together, these findings paint a picture that is difficult to dismiss. K2-18b isn't just an oddball in the galaxy. It may be one of the most promising laboratories for astrobiology we've ever found. And think about the sheer wonder of this. We are analyzing gases in the atmosphere of a planet 120 light-years away, not only detecting what is there but also drawing meaning from what is missing. This is a subtle, almost detective-like level of astronomy, where absence is as telling as presence. Just as a detective notices the dog that didn't bark, astronomers notice the ammonia that didn't appear. And sometimes, that silence speaks volumes. When scientists began piecing together the atmospheric clues from K2-18b, a new and exciting possibility emerged, one that goes beyond our usual categories of rocky Earth-like or gas giant. The data pointed toward something stranger, something we don't even have in our own solar system, a Hycean world. The term Hycean comes from combining hydrogen and ocean, and it describes a class of exoplanets proposed only in recent years. These are planets larger than Earth but smaller than Neptune, exactly the range that K2-18b falls into. For a long time, astronomers weren't sure what to make of these sub-Neptunes. Were they just failed gas giants, with thick atmospheres crushing any chance of habitability? Or could some of them actually host oceans beneath their dense skies? The Hycean hypothesis was put forward to explore this second possibility, and K2-18b now seems to fit it better than almost any other world we know. So what does a Hycean planet look like? Imagine a world cloaked in a thick, hydrogen-rich atmosphere, much thicker than Earth's but not as overwhelming as Neptune's. Beneath that atmosphere lies a global ocean, deep, dark, and vast, potentially hundreds of kilometers in depth. There are no continents, no mountain ranges, no deserts, just endless water stretching across the entire planet, hidden below clouds and gas. The surface conditions might be extreme compared to Earth, with high pressures and dim, filtered light. But within that deep ocean, shielded from radiation and stabilized by the atmosphere above, conditions could still allow life to emerge. This is where K2-18b becomes so fascinating. The combination of water vapor, methane, and carbon dioxide detected by Webb is exactly the kind of atmospheric chemistry we'd expect from a Hycean world. And the absence of ammonia, which we just explored, adds further weight to this interpretation. It suggests that the atmosphere isn't just a generic hydrogen blanket but one that may be shaped by interactions with a watery environment below. In other words, the signals we're seeing from space might be the fingerprints of a hidden ocean world. The Hycean hypothesis is revolutionary because it expands the definition of what we mean by a habitable planet. For decades, the focus has been on finding Earth-like worlds, rocky planets with thin atmospheres, orbiting sun-like stars, with oceans and continents. But those are rare, and detecting their atmospheres is extremely challenging. Hycean planets, by contrast, are more common. They seem to be one of the most abundant classes of exoplanets in the galaxy. If even a fraction of them can support life, then the odds of biology existing elsewhere in the cosmos skyrocket. And while life on a Hycean world might not look anything like life on Earth, it could still thrive. Imagine ecosystems based in dark oceans, with organisms that never see starlight but survive on chemical energy from the water-rock interactions below, much like the microbial communities around hydrothermal vents on Earth's seafloor. On our own planet, some of the most resilient and ancient forms of life are found in such environments. If Earth's deep oceans can support entire ecosystems independent of sunlight, why not K2-18b's? It's also possible that if the upper layers of K2-18b's atmosphere are mild enough, some microbial life could exist in cloud layers, floating in droplets of water or other chemicals, similar to how scientists speculate about potential life in the clouds of Venus. The beauty of the Hycean model is that it doesn't limit habitability to Earth-like conditions. It says, Life could exist in ways we've never seen before, in places we once dismissed as too alien. But there's also a scientific elegance to the Hycean idea. It explains why we're detecting the gases we are. The water vapor suggests an active ocean atmosphere exchange. The methane and carbon dioxide suggest dynamic chemistry that could be linked to biological or geochemical cycles. And the absence of ammonia points to an environment more compatible with life's chemistry. None of these signals alone would be decisive. But taken together, and viewed through the lens of the Hycean hypothesis, they form a coherent picture that makes K2-18b stand out as a serious candidate for habitability. It's worth stressing how unique this is. In our solar system, we have rocky planets, gas giants, and icy moons with subsurface oceans, but we don't have a Hycean world. The closest analogues might be moons like Europa or Enceladus, which have oceans hidden beneath thick ice crusts. But even those don't have the same hydrogen-rich atmospheres that define Hycean planets. So when we study K2-18b, we're venturing into completely uncharted territory, a type of world humanity has never directly encountered before. For astrobiology, this is a game changer. If K2-18b is indeed Hycean, it proves that life-friendly conditions might be far more common in the universe than we ever thought. Instead of focusing narrowly on Earth 2.0, we could start looking at whole new classes of planets as potential cradles of life. That dramatically widens the scope of the search and increases the odds that we'll find something. And there's something poetic about it, too. For centuries, humans have gazed at Earth's oceans as symbols of mystery and discovery. Entire civilizations rose and fell by exploring seas. Now, with K2-18b, we're looking out across the cosmos and finding oceans again. Alien oceans, unimaginably vast, hidden under skies of hydrogen. The seas of exploration are no longer on Earth. They're light years away, waiting to be understood. When astronomers first proposed the idea of Hycean planets, they weren't just inventing a new category for fun, they were fundamentally reshaping how we think about habitability in the universe. For decades, the search for life has been guided by one powerful assumption: that Earth is the model. We've been looking for planets that resemble our own, rocky, Earth-sized, with a thin nitrogen-oxygen atmosphere and oceans of liquid water on the surface. It makes sense. After all, life exists here. But as the discoveries of the past 2 decades have shown, Earth-like planets are relatively rare and incredibly hard to study. Hycean planets, by contrast, may be far more abundant, and that abundance alone makes them prime candidates in the search for extraterrestrial life. Here's why they matter so much. First, they're common. When scientists look at the catalogue of exoplanets discovered so far, a huge fraction fall into the sub-Neptune category. Planets bigger than Earth but smaller than Neptune. We don't have any in our own solar system, which once made them seem odd and unfamiliar. But now we know they might be the dominant type of planet in the galaxy. If a significant number of these sub-Neptunes are Hycean, meaning they have hydrogen-rich atmospheres and hidden oceans, then potentially habitable environments may be all around us, not rare exceptions. Second, Hycean planets are detectable in ways Earth-like planets are not. Their thick atmospheres, filled with hydrogen, are easier for telescopes like Webb to analyze. Hydrogen molecules are lighter and allow starlight to pass through more readily during transits, which means the atmospheric signals, those critical fingerprints of water vapor, methane, and carbon dioxide, are stronger and easier to detect. In contrast, the thin atmospheres of rocky, Earth-sized worlds produce faint signals that are much harder to read, even for Webb. In other words, Hycean planets are not only common, they're also more transparent to our methods of study, making them ideal candidates for atmospheric characterization. Third, Hycean worlds expand the definition of habitability. For a long time, scientists thought only Earth-like conditions could support life: a rocky surface, a breathable atmosphere, and sunlight to power ecosystems. But Hycean planets challenge that assumption. Their oceans might be deep, dark, and under high pressure, with only dim light filtering through the hydrogen skies. And yet, on Earth, life thrives in exactly such environments. In the crushing depths of our oceans, in hydrothermal vent systems that never see sunlight, and even in isolated subsurface aquifers. If life can exist here under such extremes, then why not in the vast oceans of a Hycean planet? This has profound implications for the probability of life in the universe. If we restrict our search to Earth-like planets, the odds of finding life are low, simply because such planets are rare and difficult to observe. But if we broaden the definition to include Hycean planets, the odds rise dramatically. Suddenly, entire classes of planets we once ignored become potential homes for biology. The universe doesn't just look habitable in narrow bands, it starts to look teeming with possibilities. Another reason Hycean worlds matter is their stability. Red dwarfs, like the star K2-18b orbits, are cooler and dimmer than our Sun, which places their habitable zones much closer in. That proximity makes their planets more vulnerable to stellar flares and radiation. But a Hycean world, with its thick atmosphere and deep ocean, has natural shielding. The atmosphere blocks radiation, while the ocean acts as a stable reservoir for heat and chemistry. This could make Hycean planets more resilient against the harsh environments of red dwarf systems than Earth-like planets would be. And then there's the potential diversity of life Hycean planets could host. Imagine a biosphere not driven by sunlight, like Earth's, but by chemical energy in the ocean depths. Life might not evolve plants or photosynthesis, but instead microbial mats thriving around hydrothermal vents, ecosystems based on methane or sulfur, or entirely new biochemical pathways adapted to high-pressure, hydrogen-rich conditions. If even one Hycean planet proves to host life, it would demonstrate that biology isn't limited to Earth-like scenarios. It can flourish in environments we once thought impossible. For astrobiologists, this is thrilling because it widens the scope of exploration. Instead of putting all our bets on finding another Earth, we can now think in terms of another biosphere. Life doesn't need to look like us or live as we do. It only needs stable energy sources, liquid water, or an equivalent solvent, and the right chemistry. Hycean worlds may provide all of that, even if their landscapes would look utterly alien to us. And there's a practical reason they matter, too. Hycean planets give us the best chance of finding life soon. Because they're more common and easier to study, telescopes like Webb, and future observatories like the Extremely Large Telescope, ELT, can gather meaningful data on them within our lifetimes. We don't have to wait centuries to build starships or dream of impossible missions. By pointing our telescopes at Hycean candidates, we can start answering the life question right now, with the tools we already have. So when scientists suggest that K2-18b might be a Hycean world, it's not just an interesting classification, it's a doorway. It means this planet could be part of a much larger family of worlds where biology has had the chance to arise, worlds that could number in the billions across the galaxy. Hycean planets matter because they transform the search for life from a needle-in-a-haystack problem into something much more promising. They remind us that life might not be rare or fragile. It might be robust, adaptable, and written into the fabric of planets all across the cosmos. The phrase that has electrified headlines and fueled viral videos is the bold declaration: K2-18b has a 99.7% chance of life. On the surface, that number sounds almost like a statistical verdict, like scientists ran the data, plugged in the numbers, and came back with near certainty that life exists there. It's a figure so specific, so confident, that it practically demands attention. But here's the truth. While the discoveries about K2-18b are genuinely groundbreaking, the 99.7% figure is not an official scientific consensus. Instead, it's a bold interpretation that likely emerged from a mix of scientific excitement, media amplification, and the human tendency to crave definitive answers to big mysteries. To unpack this, we first need to understand how astronomers actually talk about exoplanets. Scientists are extremely cautious when making claims about alien life. They avoid definitive percentages because the data we have is inherently indirect. We're looking at light from a star passing through a planet's atmosphere, splitting it into spectra, and identifying molecules from afar. That's an extraordinary achievement, but it's also full of uncertainties. Signal-to-noise issues, overlapping absorption features, possible contamination, and the constant risk of false positives. In other words, the evidence is powerful but not absolute. So when you hear 99.7%, you're not hearing the language of peer-reviewed astronomy, you're hearing the language of interpretation or media spin. Where might this number have come from? Some reports suggest it's rooted in early modeling studies where researchers used Bayesian statistical frameworks to compare atmospheric scenarios. In those models, certain atmospheric compositions, like the mix of water vapor, methane, and carbon dioxide alongside the absence of ammonia, lined up strongly with what we might expect from a life-supporting world, as opposed to a purely sterile chemical environment. When probabilities were run, some combinations showed very high likelihoods of aligning with a habitable, or even biologically influenced, scenario. But these models don't measure life directly. They measure how consistent atmospheric chemistry is with conditions we associate with habitability. That's a big difference. The 99.7% figure also resonates suspiciously with a statistical term known as 3 sigma confidence, often used in physics. In particle physics, for example, a 3 sigma signal suggests about a 99.7% chance that the result is real and not just random noise. However, even in that field, 3 sigma is considered suggestive, not conclusive. True discoveries typically require 5 sigma, 99.9999% certainty. It's possible that somewhere along the way, a result related to atmospheric detection confidence got translated, mistakenly or intentionally, into a sweeping claim about life. The nuance was lost, and what began as "we're 99.7% confident we've detected these molecules" became "we're 99.7% confident there's life." This is where the line between science and storytelling blurs. Scientists themselves are cautious. They'd never officially declare that K2-18b almost certainly hosts life. Instead, they frame it as, "we've detected intriguing gases, some of which are potential biosignatures, and their combination warrants further study." But when that careful statement hits the media, it can be reframed into something more sensational. Journalists, content creators, and even enthusiastic science communicators sometimes amplify the excitement into certainty, because audiences respond more strongly to bold claims than to cautious caveats. And let's be honest, people want that certainty. We want the headline that tells us, finally, we're not alone. A figure like 99.7% satisfies that craving. It gives the impression that science has delivered the definitive answer. But in reality, the truth is far more exciting in its subtlety. K2-18b isn't proof of life. It's proof that our tools have become so advanced that we can now seriously test for life on planets dozens of light-years away. That in itself is astonishing. Still, it's worth entertaining why the 99.7% claim struck such a chord. Humans respond to numbers. They carry an aura of authority. If someone says, K2-18b might host life, it sounds speculative. But if they say, K2-18b has a 99.7% chance of life, it sounds like the universe's biggest mystery has already been solved. That's why the figure went viral, regardless of whether it came from misinterpreted models, overzealous reporting, or creative embellishment. So, what should we take from this? Not that K2-18b is guaranteed to be alive, but that it is among the most promising candidates we've ever found. The actual probability of life there is unknown, possibly high, possibly low, but the atmospheric chemistry makes it impossible to ignore. The 99.7% claim is less about a definitive measurement and more about the growing confidence that we've entered a new era. We can no longer dismiss exoplanets as vague points of light. We can now characterize them in detail, debate their atmospheres, and genuinely grapple with the possibility of life. It's also a cautionary tale about how science is communicated. If we lean too heavily on exaggerated certainty, we risk eroding trust when results are refined or contradicted. But if we balance wonder with responsibility, we can inspire the public without misleading them. K2-18b's story doesn't need the 99.7% claim to be extraordinary. The truth, that we've potentially detected water vapor, methane, and carbon dioxide on a world in the habitable zone of a nearby star, is already breathtaking. In the end, the 99.7% claim reflects something deeper than statistics. It reflects our yearning for connection, our desire to know we're not alone, and our impatience to leap from possibility to certainty. It's not an official scientific conclusion. It's a cultural moment, an expression of hope wrapped in numbers. The real science is more cautious, but also more profound. We've opened a window onto alien worlds, and for the first time, what we see there hints strongly at the conditions for life. When the possibility of life on K2-18b enters the conversation, the excitement often centers around a single word: biosignatures. These are the chemical fingerprints that might betray the presence of living organisms on a distant world. They're the holy grail of astrobiology, the evidence that would transform humanity's place in the cosmos overnight. But here's the catch: Biosignatures are both powerful and perilous. For every gas or molecule that might be produced by life, there's often a non-biological process, geological, chemical, or atmospheric, that can mimic the same signal. This is why scientists tread carefully, even when Webb delivers tantalizing results. So, what counts as a strong biosignature? Traditionally, scientists look for molecules that are hard to explain without biology. On Earth, oxygen is the most obvious example. Our atmosphere is full of it, but oxygen is highly reactive. It doesn't stick around unless something keeps replenishing it. That something is photosynthesis. Plants, algae, and microbes are constantly producing oxygen, balancing the chemical books of the atmosphere. Without life, oxygen would vanish relatively quickly. That's why oxygen, especially when paired with methane, another reactive gas, has long been considered a gold standard biosignature. The coexistence of the two suggests a dynamic process, because they should cancel each other out unless something, like biology, is constantly restoring both. But exoplanets complicate the story. Oxygen might be a biosignature here on Earth, but around other stars it could also be produced abiotically. For example, the intense ultraviolet radiation from a red dwarf star can split water molecules into hydrogen and oxygen, leaving oxygen to accumulate without life's involvement. Suddenly, what looked like a smoking gun for biology becomes an ambiguous clue. This is why the biosignature debate is so intense. Context matters. The same molecule could be evidence of life in one planetary system but not in another. When it comes to K2-18b, the conversation shifts to molecules like methane, carbon dioxide, and possibly dimethyl sulfide, DMS. Methane, for instance, is a classic candidate. On Earth, a large portion of methane comes from living organisms, microbes in wetlands, the digestive systems of animals, even human agriculture. But methane can also be produced geologically, through processes like serpentinization, where water interacts with certain rocks deep underground. Detecting methane alone, therefore, isn't enough. But detecting methane alongside carbon dioxide, and especially in the absence of carbon monoxide, is intriguing. That particular mix is difficult to sustain without biological input. The potential detection of DMS is even more provocative, because on Earth, almost all of it comes from life, specifically marine phytoplankton. If Webb really saw signs of DMS on K2-18b, that would be one of the strongest biosignature candidates ever detected outside Earth. But even here, caution reigned supreme. The signal was faint, and Webb's instruments, though powerful, are still pushing their limits. Scientists must analyze and reanalyze the data, rule out noise, and confirm that what looks like DMS isn't just a statistical blip or an artifact of the models. This is where scientific caution comes into play. History has taught astronomers to be wary of rushing to conclusions. Mars, for instance, has repeatedly teased us with methane detections, only for those detections to fade or be explained by non-biological processes. Venus, too, made headlines when a potential detection of phosphine, a gas thought to be a biosignature, set the scientific community buzzing. But follow-up studies questioned whether the signal was real at all, or whether phosphine could be produced by unknown chemistry in Venus's hostile atmosphere. These episodes serve as reminders. Extraordinary claims require extraordinary evidence, and the road from detection to confirmation is long and fraught with pitfalls. That's why scientists dealing with K2-18b are careful not to say, "We've found life." Instead, they frame their findings in terms of plausibility. We've found gases consistent with habitability, and some of them could be biosignatures. It's a subtle but crucial difference. The scientific method demands that all non-biological explanations be ruled out before life becomes the default explanation. And because planets are complex systems, with geology, atmospheres, chemistry, and radiation all interacting in ways we don't fully understand, ruling out every possibility is extraordinarily difficult. This caution isn't a lack of imagination, it's a safeguard. The discovery of extraterrestrial life would be the most profound in human history. It would reshape philosophy and science. With stakes that high, scientists must be absolutely certain. A premature declaration that turns out to be wrong could set back the field, damage public trust, and overshadow genuine breakthroughs. So, they move carefully, testing and retesting, comparing models, and inviting skepticism. But make no mistake, the debate itself is thrilling. For the first time, we're not asking abstract questions like could life exist elsewhere? We're looking at actual planets, with actual atmospheres, and weighing the evidence. The fact that K2-18b even raises the possibility of biosignatures shows how far we've come. 20 years ago, we didn't even know exoplanets were common. Today, we're debating the chemical fingerprints of life on a world 120 light-years away. That's a staggering leap in human capability. So when you hear the word biosignature in connection with K2-18b, remember, it doesn't mean proof of life. It means a clue, a possibility, a direction for further investigation. It's like finding a footprint in the sand. It could belong to a person, or it could be an odd pattern carved by the wind. Scientists must figure out which it is. And that takes time, data, and rigorous skepticism. But the very fact that we're finding footprints at all, on planets so far away, is a triumph in itself. One of the most electrifying developments in the study of K2-18b is the possible detection of dimethyl sulfide, or DMS, in its atmosphere. On Earth, DMS is almost exclusively produced by life, primarily by marine phytoplankton as part of the sulfur cycle. It's a molecule that, in terrestrial terms, is practically synonymous with biological activity. The idea that it might exist on a planet over 120 light-years away is enough to make any astrobiologist's heart race, and it has sparked widespread excitement across both the scientific community and the public. DMS is fascinating because of its specificity. Unlike methane, which can be generated by geological processes, DMS on Earth is overwhelmingly biological in origin. Tiny microorganisms in the oceans metabolize sulfur-containing compounds and release DMS as a byproduct. It's a key player in Earth's climate, contributing to cloud formation by acting as a nucleus around which water droplets condense. But beyond its ecological role, its near-exclusive association with life makes it a potential biosignature of extraordinary significance. Detecting it anywhere else would immediately raise the question, could biology exist there, too? Webb's instruments, especially the Near-Infrared Spectrograph (NIR spec), have the sensitivity to detect faint spectral lines associated with molecules like DMS. In the spectra collected from K2-18b, researchers noticed subtle absorption features at wavelengths where DMS should appear. These features are weak, but they are consistent with the molecular fingerprints of DMS. This is not a casual observation. It is the type of signal that makes researchers sit up and double-check everything. Confirming DMS would be a monumental step, potentially placing K2-18b among the most promising candidates for habitability we've ever identified. However, this is also where caution is paramount. The data is still tentative, and the signal could have multiple explanations. Atmospheric chemistry, instrumental noise, or overlapping spectral features from other molecules could all mimic the presence of DMS. Scientists must carefully rule out false positives before making any claims. After all, the history of exoplanet research is littered with tantalizing signals that later proved to be artifacts. Phosphine on Venus is the perfect cautionary tale. What initially appeared to be a groundbreaking biosignature became controversial as more data and alternative chemical pathways were considered. If DMS on K2-18b is real, the implications are profound. This molecule would strengthen the idea that the planet may be a Hycean world, with a deep ocean and hydrogen-rich atmosphere. On Earth, DMS is produced in aquatic environments, and its presence in the atmosphere is linked to a functioning biological cycle in the oceans. If a similar mechanism is at play on K2-18b, it suggests the possibility of life in its hypothetical global oceans, perhaps microbial in nature, interacting with its atmosphere in ways that produce detectable chemical signatures. Yet, even if DMS is present, it may not guarantee life in the way we imagine it. Exoplanetary environments are alien, and chemistry can behave differently under high pressures, exotic temperatures, and unique atmospheric compositions. There could be unknown abiotic pathways that produce DMS under conditions unlike anything on Earth. That's why the scientific community emphasizes verification, repeated observations, and rigorous modeling to ensure that this is truly a biosignature and not a chemical coincidence. The excitement surrounding DMS is also symbolic. For decades, astrobiologists have debated how to detect life beyond Earth, and many have concluded that single-molecule detections are rarely sufficient. Instead, scientists look for combinations of molecules that together suggest biological activity. In K2-18b, DMS would join water vapor, methane, and carbon dioxide, creating a compelling ensemble of chemicals that collectively hint at the possibility of life. In essence, DMS could act as the capstone molecule in a growing puzzle, one that increasingly points to a potentially habitable and biologically active world. The broader impact of this potential detection is staggering. If confirmed, it would be the first time humanity has found a molecule almost uniquely tied to life on Earth on a planet light years away. It would provide the first tentative glimpse of extraterrestrial biology, even if only at a microbial scale. Imagine looking up at the night sky and knowing that, somewhere out there, molecules produced by life are drifting in the atmosphere of another world. It would be a profound shift in how we perceive our place in the universe. At the same time, this is a humbling moment for science. The possible detection of DMS reminds us that even the most extraordinary claims require rigorous verification. Webb has opened a door, but stepping through it requires careful steps. More observations, cross-checking with other instruments, modeling atmospheric chemistry, and ruling out all plausible non-biological explanations. Only then can the scientific community responsibly discuss DMS as a true potential biosignature. In short, DMS is both thrilling and cautionary. It's a molecule that could revolutionize our understanding of life in the cosmos, yet it demands the utmost scrutiny before we claim its significance. In K2-18b, we may be glimpsing the chemical whisper of an alien ocean, but the conversation is just beginning. The possible detection of DMS is not a proclamation that life exists. It's a spark of hope, the kind of tantalizing hint that keeps scientists, and all of humanity, looking up at the stars with wonder and determination. While the possible detection of dimethyl sulfide, DMS, on K2-18b has captured the imagination of both scientists and the public, it is crucial to underscore the importance of scientific skepticism in this context. The excitement surrounding DMS is palpable, but excitement alone cannot replace rigorous verification. In astronomy, particularly in the study of exoplanet atmospheres, caution is not just prudent, it is fundamental. A single misinterpretation could create headlines claiming we found life, only for later analysis to reveal that the signal was ambiguous, misread, or caused by other atmospheric processes. The first reason for skepticism is signal strength and noise. The features attributed to DMS in Webb spectral data are incredibly faint, often at the edge of what the telescope can reliably detect. Even with Webb's unprecedented sensitivity, interpreting these subtle absorption lines is challenging. Small fluctuations in the data, instrumental noise, or even interference from the host star's light can produce signals that mimic the spectral fingerprint of a molecule. Astrophysicists must carefully differentiate between real molecular signatures and artifacts that could be introduced by the telescope or data processing techniques. Secondly, there's the challenge of overlapping molecular signatures. Many molecules absorb light at similar wavelengths. Methane, ammonia, sulfur compounds, and even some exotic chemicals in hydrogen-rich atmospheres can produce absorption features that partially overlap with the spectral lines expected for DMS. Disentangling these overlapping signals requires sophisticated models, extensive simulations, and repeated observations. One spectrum alone is rarely enough to confirm the presence of a molecule, especially one as extraordinary as DMS. Third, and perhaps most importantly, scientists must rule out alternative, non-biological explanations. While DMS on Earth is almost exclusively biological, K2-18b is not Earth. It has a hydrogen-rich atmosphere, high pressures, potentially extreme temperatures, and chemistry that we can only approximate with models. It's possible that unknown abiotic chemical reactions, catalyzed by unique conditions on the planet, could produce DMS-like molecules. Until these possibilities are systematically tested and ruled out, any claim of life remains tentative. This cautious approach is a hallmark of credible science. History provides ample examples of why such skepticism is warranted. Consider the phosphine saga on Venus. Initial detections generated headlines suggesting possible life in the planet's clouds, only for follow-up studies to cast doubt on the signal and raise alternative chemical explanations. Similarly, methane detections on Mars have been inconsistent and debated for decades, sometimes showing up and disappearing depending on the instrument and the season. Each case illustrates how preliminary findings, while exciting, can be misleading if not verified through repeated, independent observations. In the case of K2-18b, the scientific process is methodical. Researchers are reanalyzing the spectra, applying updated models, and planning additional transits to observe the planet under different conditions. Only with multiple confirmations, ideally using different instruments and wavelengths, can the presence of DMS move from a tantalizing possibility to a robust claim. Peer review and independent verification are critical. The moment a discovery is announced, other teams around the world will scrutinize the data, replicate the analyses, and either reinforce or challenge the findings. This iterative, self-correcting process is how science separates hope from evidence. It's also worth noting that skepticism does not diminish the significance of the potential DMS detection. On the contrary, it enhances it. The fact that scientists are debating this molecule in detail means that K2-18b is a compelling target for astrobiology. Even if the DMS signal ultimately turns out to be non-biological, the mere possibility has already reshaped how we think about sub-Neptune worlds and Hycean planets. It drives the development of more precise instruments, motivates further observations, and fuels the theoretical work needed to interpret complex atmospheres. Public enthusiasm must also be tempered by scientific caution. Headlines claiming a 99.7% chance of life based on DMS alone are misleading. Responsible communication involves explaining both the potential significance and the uncertainties. Scientists emphasize phrases like consistent with potential biosignatures rather than proof of life. It is this balance of excitement and rigor that ensures discoveries are credible, reproducible, and ultimately transformative. Finally, skepticism is not a barrier to discovery, it's a pathway to certainty. By scrutinizing the data, modeling every alternative explanation, and awaiting corroboration, researchers strengthen the confidence of any eventual conclusion. K2-18b's possible DMS is a spark, a hint that life might exist beyond Earth. But it will only become a reliable beacon once it survives the scrutiny of scientific skepticism, repeated observations, and rigorous analysis. In summary, the potential detection of DMS on K2-18b is thrilling, but the scientific community is approaching it with measured caution. The data is being verified, models are being refined, and alternative explanations are being rigorously tested. This skepticism is not pessimism, it is the cornerstone of credible science. Only through this careful, methodical approach can we hope to transform tantalizing hints into profound knowledge about the possibility of life beyond our planet. Even with the most tantalizing chemical detections, scientists always have to consider the possibility of false positives. Signals that appear to indicate life but are actually the result of entirely natural, non-biological processes. This is especially true for planets like K2-18b, where the atmosphere is unlike anything on Earth, and chemical reactions can behave in ways we may not fully anticipate. Understanding false positives is critical because it prevents premature claims and keeps the scientific investigation grounded in evidence. Take methane, for example. On Earth, it's strongly associated with life. Microbes produce vast amounts of it in wetlands, the ocean, and even in the digestive tracts of animals. Yet methane can also be created abiotically through serpentinization, a chemical reaction between water and certain types of rock containing iron and magnesium. In this process, water infiltrates subsurface rocks, reacts chemically, and releases methane as a byproduct. On a planet like K2-18b, which likely has a thick hydrogen-rich atmosphere and high-pressure layers overlying a potential ocean, such geological processes could be far more prevalent than on Earth. Methane alone, therefore, cannot definitively point to life. Similarly, water vapor and carbon dioxide, both detected on K2-18b, can have entirely non-biological origins. Water vapor may come from evaporation off a global ocean or from the planet's interior, while carbon dioxide can accumulate through volcanic outgassing or interactions between water and rocks. On Earth, these gases are part of life cycles, but on K2-18b, they could simply reflect the planet's chemistry and physics. Alone, they are not biosignatures, but when considered together with other molecules like methane or DMS, they create patterns that are suggestive, though not conclusive. Dimethyl sulfide, DMS, is often cited as one of the most compelling biosignatures because it is almost exclusively biological on Earth. Yet scientists remain cautious because we cannot fully rule out unknown abiotic pathways on alien worlds. Extreme pressures, temperatures, and hydrogen-rich atmospheres could catalyze chemical reactions that produce molecules mimicking DMS, even in the absence of life. Without a complete understanding of K2-18b's unique environment, any detection must be considered provisional. Another class of false positives arises from photochemistry. Red dwarf stars, like the one K2-18b orbits, emit high levels of ultraviolet radiation. This radiation can break down molecules in ways that create reactive species, forming gases like methane, carbon monoxide, or even more exotic compounds. Some of these could appear in spectra as features we might otherwise interpret as biosignatures. Similarly, cloud layers, atmospheric mixing, or temperature gradients can distort signals, making it tricky to interpret spectral data accurately. The lesson is that context is everything. Scientists look for chemical combinations that are difficult to produce without biological activity. For instance, the simultaneous presence of methane and carbon dioxide, particularly with little or no carbon monoxide, is less easily explained by non-biological chemistry. Likewise, the absence of ammonia on K2-18b strengthens the case that the atmosphere is unusual and may be conducive to life, but it is not a guarantee. Multiple lines of evidence, cross-verified across different observations, are needed to confidently rule out false positives. Historically, false positives have shaped the cautious approach of astrobiology. Consider the repeated methane detections on Mars. Some early measurements suggested seasonal spikes, hinting at possible microbial activity. Later studies showed that these could also be explained by underground chemical reactions or instrument artifacts. Similarly, the claimed detection of phosphine in Venus's atmosphere initially excited scientists but faced intense scrutiny as alternative chemical explanations were proposed. These cases illustrate that apparent biosignatures can be deceptive, and premature conclusions can mislead both the scientific community and the public. For K2-18b, researchers are acutely aware of these pitfalls. Each spectral signature is analyzed with sophisticated atmospheric models to test whether it could arise abiotically. They simulate chemistry under high pressures and temperatures, explore photochemical pathways, and examine the effects of clouds and hazes. Only after exhausting all plausible non-biological explanations can the argument for life become stronger. Until then, any claim remains provisional, a hypothesis to be tested, not a confirmed fact. The possibility of false positives also highlights the need for complementary observations. Webb alone provides unprecedented spectral data, but corroborating evidence from other telescopes, like the Extremely Large Telescope, ELT, or upcoming space missions, will be essential. Observing multiple transits, using different spectral bands, and comparing K2-18b with similar planets helps build a more robust understanding and reduces the risk of misinterpretation. In essence, false positives are a reminder that the search for life is as much about ruling out natural explanations as it is about finding extraordinary ones. K2-18b may be one of the most promising candidates yet, but scientists proceed with caution, carefully balancing excitement with methodological rigor. Only by acknowledging the potential for natural, non-biological processes can we ensure that when life is finally detected, the claim is truly credible, and the discovery monumental. When we look at K2-18b's atmosphere, it's natural to compare it with Earth's. After all, Earth is the only planet we know of that supports life, and its atmosphere provides a clear reference point. Yet the comparison reveals both striking similarities and profound differences, highlighting how alien K2-18b truly is, even while tantalizingly suggesting potential habitability. Earth's atmosphere is predominantly nitrogen, about 78%, and oxygen, about 21%, with trace amounts of carbon dioxide, methane, water vapor, and other gases. This composition is the result of billions of years of geological and biological activity. Oxygen, for instance, accumulates due to photosynthesis, while methane is produced both biologically and geologically, and water vapor cycles constantly between the oceans, atmosphere, and land. The delicate balance of these gases creates the temperate climate and stable conditions that make life possible. In contrast, K2-18b is a sub-Neptune, much larger than Earth, with a likely hydrogen-rich atmosphere that dominates its envelope. Hydrogen is a light, reactive gas that is relatively rare in Earth's atmosphere, but on K2-18b, it likely forms the bulk of the atmosphere, creating pressures and chemistry that are alien to us. This hydrogen-dominated environment fundamentally changes how other molecules behave. For instance, water vapor, methane, and carbon dioxide on K2-18b exist in proportions and under conditions very different from what we see on Earth. Yet their presence hints at a familiar chemical network where life could, hypothetically, influence atmospheric composition. One similarity to Earth is the presence of water vapor. On Earth, water vapor is critical for climate regulation and life, forming clouds and driving the hydrological cycle. On K2-18b, Webb has detected water vapor in the atmosphere. While we don't yet know whether it condenses into clouds or cycles back into oceans as on Earth, its very presence in the habitable zone suggests a potential medium for life. Water is, after all, the universal solvent that allows biochemistry to function. The detection of water vapor on a hydrogen-rich sub-Neptune is unusual but encouraging because it may indicate a planet with stable, liquid reservoirs beneath the thick atmosphere. Methane is another point of comparison. On Earth, methane is a byproduct of both geological and biological processes, and it interacts with oxygen to maintain a dynamic chemical balance. On K2-18b, methane has been detected alongside carbon dioxide but without oxygen, which makes the chemistry alien yet potentially interesting for life. Without oxygen, methane is more stable and can persist longer, but its coexistence with carbon dioxide in detectable quantities raises the question of whether some active process, perhaps biological, perhaps geochemical, is replenishing it, much as Earth's biosphere continually sustains its own methane levels. Carbon dioxide is also present on both planets, but the context is different. On Earth, CO is a minor but crucial component, regulating climate and supporting the carbon cycle. On K2-18b, it may be more abundant relative to other gases, potentially forming a greenhouse effect that keeps any deep oceans from freezing under the faint light of a red dwarf. While this CO doesn't indicate life on its own, it is a critical part of the atmospheric puzzle, just as it is on Earth. One key difference, however, is the absence of ammonia on K2-18b. Earth has very little ammonia in the atmosphere because nitrogen is largely bound in N or incorporated into biological molecules. The lack of ammonia on K2-18b is intriguing because, in a hydrogen-rich atmosphere, ammonia might be expected in significant amounts. Its absence could suggest chemical conditions more compatible with life, much as Earth's atmosphere is tuned in ways that stabilize life-friendly chemistry. The potential detection of DMS further differentiates K2-18b from Earth. On our planet, DMS is almost entirely biological, produced by phytoplankton. Its detection, or even tentative detection, on K2-18b suggests a biochemical pathway that is not only rare but perhaps analogous to Earth's ocean-based life. If confirmed, it would be one of the strongest points of similarity in terms of chemical signatures. Pressure and temperature, however, are extreme differences. Earth has a solid surface and moderate pressures, whereas K2-18b's thick hydrogen envelope likely creates high-pressure conditions at lower altitudes, with temperatures that could vary dramatically depending on atmospheric depth. Earth-like life would struggle under such conditions, but extremophiles on Earth, microorganisms thriving near hydrothermal vents or deep in icy oceans, show that life can adapt to extreme environments. This reinforces the idea that habitability is not solely defined by Earth-like conditions but by the presence of liquid solvents, energy sources, and chemical cycles. In summary, comparing K2-18b's atmosphere to Earth's shows both promise and caution. Water vapor, methane, and carbon dioxide echo familiar chemistry, hinting at the possibility of habitable processes. Yet the dominant hydrogen atmosphere, potential high pressures, and alien chemical context remind us that K2-18b is not a twin of Earth, it is something entirely new. This blend of similarity and difference makes it one of the most compelling targets in the search for life, providing a laboratory to test our understanding of how life could exist under conditions radically different from our own. One of the major challenges in assessing K2-18b's habitability lies in its classification as a sub-Neptune. Unlike Earth, which has a solid surface that provides a stable platform for oceans, continents, and the development of life, K2-18b exists in a category of planets that may lack a traditional solid surface entirely. Its larger size, roughly 2.6 times the radius of Earth, and likely composition suggest a thick envelope of hydrogen and helium surrounding a denser, potentially icy or rocky core. This layered structure creates complications when considering how life could arise or persist. A planet without a solid surface fundamentally changes the equation for habitability. On Earth, life began and evolved on land and in shallow oceans, where interactions with minerals, temperature gradients, and sunlight drove chemical evolution. These interfaces between solid, liquid, and gas provide catalytic environments for prebiotic chemistry. In contrast, on a sub-Neptune like K2-18b, the upper layers we observe are predominantly gaseous, dominated by hydrogen with water vapor, methane, and carbon dioxide mixed in. If the planet lacks a firm, stable surface, any potential life would need to exist entirely within the ocean or perhaps suspended in the upper atmosphere, environments that are dramatically different from Earth. Pressure is another complicating factor. Beneath K2-18b's thick hydrogen atmosphere, pressures increase rapidly, potentially reaching levels hundreds of times higher than Earth's surface. High pressure changes the behavior of water and other solvents. It could keep oceans in a supercritical state, where the distinction between liquid and gas disappears, or form exotic high-pressure ices at the base of the ocean. While extremophiles on Earth demonstrate that life can tolerate high pressures, these extreme conditions may limit the types of biochemical processes that are possible. Temperature is equally complex. The atmosphere of K2-18b is subject to both heating from its host star, a red dwarf, and the greenhouse effect caused by gases like carbon dioxide and methane. The balance between heating and radiative cooling determines whether there is a liquid water layer at all, and if so, how deep it lies. Even if water exists in liquid form somewhere beneath the atmosphere, the surface conditions we measure may be far hotter or colder than Earth, making it difficult to extrapolate directly from terrestrial life. Another consideration is atmospheric dynamics. K2-18b's thick hydrogen envelope may create strong winds, violent storms, and complex circulation patterns that mix gases and heat throughout the atmosphere. This could disperse chemicals like water vapor or DMS, making it more challenging for localized ecosystems to persist. On Earth, ecosystems benefit from relative stability in certain regions, the ocean floor, shallow reefs, and continental shelves. But K2-18b might be a far more turbulent environment, with fewer protected niches for life to take hold. Furthermore, the lack of a solid surface affects nutrient cycling. On Earth, rocks and soil provide minerals and elements critical for biology. Subduction, erosion, and volcanic activity recycle these nutrients into the oceans and atmosphere, sustaining life over geological timescales. If K2-18b has a deep liquid ocean atop a possibly icy or partially molten core, the mechanism for cycling nutrients may be quite different or less efficient. Life would need to adapt to an environment where nutrient replenishment could be slow or highly uneven. Finally, the classification as a sub-Neptune raises questions about planetary formation and history. Many of these planets are thought to have accumulated thick hydrogen-helium envelopes early in their formation, which could have trapped heat and prevented the formation of a conventional solid surface. Over billions of years, some sub-Neptunes may lose part of this atmosphere through stellar radiation, but others retain it, leaving a persistent barrier between the deeper ocean or rocky interior and the observable atmosphere. This means that even if life exists beneath the clouds, detecting its signatures becomes more difficult, because the thick gaseous layer can obscure or dilute the chemical signals that Webb observes. In summary, K2-18b's status as a sub-Neptune presents unique challenges to habitability. The absence of a solid surface, extreme pressures, potential temperature gradients, turbulent atmospheric dynamics, and complex nutrient cycles all complicate the picture. Life, if it exists, would need to be fundamentally different from terrestrial life, adapted to survive in oceans beneath thick hydrogen atmospheres rather than on a solid crust exposed to sunlight. Yet these very challenges also make K2-18b fascinating. It forces scientists to expand their definition of habitability and consider entirely new forms of biology that could thrive in environments far removed from Earth's familiar landscape. One of the most compelling ideas about K2-18b is the possibility that, beneath its thick hydrogen-rich atmosphere, it may host deep, global oceans, immense bodies of liquid water or water-rich solutions that could provide a haven for life. While the planet's surface is unlike Earth's, with no visible landmass and extreme pressures at lower altitudes, the oceans hidden beneath the atmospheric envelope represent one of the most promising environments for habitability. These oceans could act as buffers, protecting potential life from the harsh conditions above while providing the chemical environment necessary for biological processes. The concept of deep oceans on K2-18b is strongly tied to its classification as a Hycean world. In this model, the thick hydrogen atmosphere exerts pressure on the underlying layers, allowing water to remain liquid even at depths where temperatures might otherwise cause it to freeze or vaporize. These oceans might be hundreds of kilometers deep, vastly exceeding the depth of Earth's oceans, which average around 4 kilometers. A deep ocean of this kind provides an enormous volume for chemical reactions, increasing the chances that life could emerge or persist. The protective role of these oceans cannot be overstated. K2-18b orbits a red dwarf star, which is smaller and cooler than our Sun but prone to stellar flares and intense ultraviolet radiation. At the surface, these flares could be lethal to life as we know it. But deep beneath the water, life could be shielded from radiation, much like extremophiles on Earth thrive in the dark depths of our oceans near hydrothermal vents. In this way, the oceans could serve as both a cradle and a refuge, providing a stable environment for biochemistry to occur. A deep ocean also enables chemical gradients, which are essential for life. On Earth, hydrothermal vents on the seafloor generate rich chemical energy by interacting with the surrounding rock. These gradients drive metabolic processes, enabling microbial life to thrive in complete darkness. K2-18b might host similar vent-like regions if its ocean interacts with a rocky or icy core beneath the hydrogen envelope. Such interactions could produce methane, hydrogen, or other compounds that life could exploit, creating ecosystems independent of sunlight. The presence of water vapor in K2-18b's atmosphere, detected by the James Webb Space Telescope, lends credence to the idea of deep oceans. Water vapor implies an active water cycle or exchange between the liquid and gaseous layers. While we cannot yet observe these oceans directly, the atmospheric signals suggest that water is abundant and mobile, an essential prerequisite for habitability. The chemistry of methane, carbon dioxide, and possible DMS may also indicate that these oceans are not inert. They could be sites of complex chemical or even biological activity. Another fascinating aspect of K2-18b's oceans is their potential diversity of habitats. Unlike Earth, which has a relatively shallow ocean atop a solid crust, K2-18b's ocean may have layers with varying temperatures, pressures, and chemical compositions. The upper layers might interact with the atmosphere, exchanging gases like methane, water vapor, and carbon dioxide. Deeper layers might approach high-pressure phases of water or ice, creating gradients that could sustain life in specialized niches. This stratification could allow multiple forms of life, or complex biochemical networks, to coexist, even without a solid surface. The oceans also enhance the potential detectability of life. If life exists in these oceans, it may release gases into the atmosphere, where Webb and future telescopes can detect them. Molecules like methane and DMS, produced in a deep ocean and diffusing upward, could serve as biosignatures, signaling biological activity far above the water. In other words, these oceans could act as hidden laboratories for life while still leaving traces for us to detect light years away. However, the extreme depth and pressure of K2-18b's oceans also pose challenges. Life would have to adapt to high-pressure conditions, possibly favoring microbial or unicellular organisms rather than complex life forms. Nutrient cycling might be slower, and energy sources more limited than on Earth. But extremophiles on our own planet show that life can thrive in conditions once thought uninhabitable, from deep-sea hydrothermal vents to acidic hot springs. The oceans of K2-18b could be a vast, alien version of these resilient ecosystems. In short, the potential for deep oceans makes K2-18b one of the most compelling candidates for extraterrestrial life. These oceans offer stability, protection, and chemical richness, all of which are essential for habitability. While the planet's thick atmosphere and high pressures present challenges, they also create conditions that could sustain life in forms entirely different from what we know on Earth. The oceans may be hidden from direct view, but their presence could turn K2-18b into a world where biology, perhaps microbial, perhaps more complex, could flourish in the depths beneath the clouds. If we entertain the possibility that K2-18b hosts life, the question naturally arises: what form could that life take? Because the planet is a sub-Neptune with a hydrogen-rich atmosphere and likely deep global oceans, the scenarios differ significantly from what we're accustomed to on Earth. Our speculation must account for the extreme pressures, potential high temperatures, and absence of a solid surface in most regions, while also considering the chemical and energy environments that Webb has begun to reveal. The most plausible form of life would likely be microbial, much as early life on Earth was. Microorganisms are resilient, adaptable, and capable of surviving under conditions that would be lethal to larger, multicellular organisms. On K2-18b, microbes could exist in the oceans beneath the thick atmosphere, relying on chemical gradients for energy rather than sunlight. Hydrothermal vents or interactions between water and the rocky core could provide hydrogen, methane, and other chemicals that serve as metabolic fuel. These organisms could form vast microbial mats, floating colonies, or biofilms, establishing ecosystems entirely independent of light. Another possibility is that K2-18b harbors oceanic plankton-like organisms. If life evolved in the upper layers of the ocean, where some interaction with the atmosphere occurs, it might produce molecules like methane or DMS that escape into the hydrogen-rich atmosphere and could eventually be detected by telescopes. This would be analogous to Earth's phytoplankton, which thrive in the ocean's sunlit layers and significantly influence atmospheric chemistry. Even though K2-18b likely receives far less visible light than Earth, life could exploit alternative energy sources, such as chemical gradients or tidal heating, to sustain metabolism. There's also the tantalizing, though less likely, scenario of complex life. On Earth, multicellular organisms required stable environmental conditions, abundant energy sources, and a solid surface or stable substrate to anchor themselves. K2-18b's thick atmosphere and deep oceans make such development challenging, but not impossible. Imagine vast, slow-moving, gelatinous creatures adapted to high pressures, drifting in the global ocean. Life could evolve to exploit gradients of temperature, chemicals, or currents, forming predator-prey-like dynamics entirely unlike terrestrial ecosystems. While this is highly speculative, the sheer depth and volume of the oceans provide the physical space necessary for evolutionary experimentation over billions of years. One unique possibility for K2-18b is floating or aerial life within the atmosphere itself. In its dense hydrogen envelope, buoyant organisms could exist suspended in the upper layers of the atmosphere, similar to theoretical models proposed for Venus clouds or gas giants. These organisms could metabolize chemicals in the gas layer, perhaps using methane or carbon dioxide as energy sources, and could even contribute to detectable biosignatures without touching the ocean below. This scenario stretches our imagination but is consistent with the planet's atmospheric dynamics and chemical composition. Microbial and oceanic life also raise intriguing questions about biogeochemical cycles. On Earth, life shapes the atmosphere over billions of years. If life exists on K2-18b, even at a microbial scale, it could influence the atmospheric composition by producing or consuming gases like methane, DMS, or other organosulfur compounds. These interactions could explain some of the chemical signatures Webb has observed, including the tantalizing combination of water vapor, methane, and potential DMS. In essence, life could leave a detectable imprint without ever evolving complex structures. Finally, life on K2-18b might be radically different from Earth life, exploiting chemistries and energy sources we haven't yet considered. The planet's hydrogen-rich atmosphere, high pressure, and possible exotic ocean chemistry could allow organisms to use alternative biochemistries, perhaps silicon-based frameworks or ammonia water solvents in deeper layers. While speculative, this possibility underscores that habitability is not limited to Earth analogues. Microbial life, if it exists, might be perfectly suited to conditions that would appear inhospitable to us, thriving in ways that stretch our understanding of biology. In summary, if K2-18b harbors life, the most likely forms are microbial or oceanic, adapted to survive in deep oceans beneath a thick atmosphere. Floating or aerial life is a more speculative but fascinating possibility, and complex life, while improbable, cannot be completely ruled out given billions of years for evolution. The key takeaway is that life, if present, may be vastly different from terrestrial life yet capable of leaving detectable chemical signatures that Webb and future telescopes could observe. This opens the door not just to the discovery of life, but to the understanding of entirely new biological paradigms, expanding our imagination of what living systems can be. The James Webb Space Telescope, having already provided tantalizing glimpses of K2-18b's atmosphere, is only at the beginning of what could become a revolutionary exploration of this intriguing world. The next steps involve targeted, high-precision observations that aim to refine our understanding of its atmospheric composition, probe its chemical complexity, and evaluate the potential for habitability in much greater detail. Webb's instruments are uniquely suited for this, combining sensitivity, spectral resolution, and coverage across a wide range of infrared wavelengths. One of the first priorities is to observe additional transits of K2-18b. Each time the planet passes in front of its host star, starlight filters through the planet's atmosphere, leaving spectral fingerprints of the gases present. Multiple transits allow astronomers to increase signal-to-noise ratios, distinguishing real molecular signals from statistical fluctuations or instrumental artifacts. By stacking data from numerous transits, scientists can more confidently detect faint features like dimethyl sulfide, DMS, methane, or trace gases that may indicate biological or geochemical activity. Another key approach involves expanding the spectral range of observations. Webb can examine light in the near and mid-infrared, capturing the subtle absorption features of a variety of molecules. For instance, water vapor, methane, carbon dioxide, and ammonia each absorb light at specific wavelengths. By mapping these features across multiple bands, scientists can create a more complete molecular inventory of K2-18b's atmosphere. Detecting multiple gases simultaneously and determining their relative abundances helps to distinguish between biological and abiotic processes. For example, the balance of methane and carbon dioxide could indicate whether a replenishing source exists, hinting at possible metabolic activity. JWST can also conduct phase curve observations, tracking K2-18b as it orbits its star. These observations allow researchers to map temperature variations, atmospheric circulation, and even cloud distributions across the planet. Understanding the dynamics of its hydrogen-rich atmosphere is critical, because turbulent mixing, winds, and temperature gradients can influence the chemical signatures we observe. For example, a molecule detected in one layer of the atmosphere might not be representative of the deeper ocean beneath. By correlating chemical abundances with atmospheric dynamics, astronomers can refine models of potential habitats and identify regions where life could plausibly exist. A particularly exciting future observation involves searching for seasonal or temporal variations in atmospheric composition. On Earth, the abundance of certain gases fluctuates seasonally due to biological cycles, volcanic activity, or temperature changes. If K2-18b exhibits analogous variations, especially in molecules like methane or DMS, it could provide stronger evidence for active processes, whether biological or geochemical. Detecting consistent patterns over time would help scientists rule out transient signals caused by flares, instrument noise, or short-term chemical anomalies. JWST will also focus on high-resolution spectroscopy to better resolve overlapping molecular features. This is especially important for molecules like DMS, which share spectral regions with other gases. By teasing apart these subtle features, astronomers can confirm or refute tentative detections and potentially identify new compounds that have so far eluded detection. These high-resolution observations could even hint at isotopic ratios, which might provide clues about the sources of certain molecules, whether they arise from biological activity, photochemistry, or geological processes. Finally, Webb's observations will be coordinated with theoretical modeling and laboratory studies. Spectroscopic data alone cannot reveal the full story. Scientists must interpret it in the context of planetary chemistry, pressure-temperature profiles, and potential biological mechanisms. Laboratory experiments simulating high-pressure hydrogen-rich atmospheres help determine which molecules could be produced abiotically, which strengthens the confidence of any biological interpretation. The combination of observational data and modeling creates a robust framework for assessing habitability. In summary, the next steps with JWST involve repeated, high-precision transits, expanded spectral coverage, phase curve mapping, temporal monitoring, and high-resolution spectroscopy. Each of these approaches builds on the initial findings, refining our understanding of K2-18b's atmosphere and its potential for life. Webb is not just capturing a snapshot of this planet, it is laying the groundwork for a dynamic, multidimensional picture of an alien world, allowing us to explore its chemical complexity, atmospheric behavior, and, perhaps one day, signs of life beneath its clouds. While the James Webb Space Telescope is revolutionizing our view of exoplanet atmospheres, the search for life on K2-18b will be greatly enhanced by next-generation observatories, both in space and on the ground. One of the most anticipated of these is the Extremely Large Telescope, ELT, currently under construction by the European Southern Observatory in Chile. With its 39-meter primary mirror, the ELT will collect unprecedented amounts of light, allowing it to probe distant exoplanets with a level of detail impossible with current telescopes. The ELT, along with other upcoming ground-based giants like the Giant Magellan Telescope, GMT, and the 30-meter telescope, TMT, will be capable of directly imaging exoplanets and analyzing their atmospheres using advanced spectrographs. For a planet like K2-18b, these telescopes can complement Webb's transit observations by observing the planet at different orbital phases, potentially detecting reflected light from the planet itself or measuring thermal emission. This would provide additional information about the planet's temperature profile, cloud coverage, and atmospheric composition, helping to verify or refine Webb's findings. One of the key advantages of telescopes like the ELT is their ability to resolve fine spectral details. Webb has already revealed the presence of water vapor, methane, and carbon dioxide in K2-18b's atmosphere, but distinguishing between overlapping molecular features, especially faint ones like dimethyl sulfide, requires higher spectral resolution. Ground-based observatories equipped with adaptive optics can achieve this, helping to confirm tentative biosignatures and detect additional molecules that might indicate habitability. In addition to spectroscopy, the ELT could contribute to time-resolved observations of K2-18b. By monitoring changes in the atmosphere over multiple rotations or orbits, astronomers can study weather patterns, cloud formation, and possible seasonal variations. Such data would help scientists understand how gases like methane, DMS, or water vapor are distributed and whether they fluctuate in ways that could hint at biological activity. These observations, when combined with Webb's transits, would create a multi-layered view of K2-18b's atmosphere. Beyond the ELT, upcoming space-based missions like Ariel, Atmospheric Remote Sensing Infrared Exoplanet Large Survey, planned by the European Space Agency, will focus specifically on exoplanet atmospheres. Ariel will survey hundreds of planets, including sub-Neptunes like K2-18b, to determine the prevalence of key molecules, cloud coverage, and thermal structures. The combination of Webb, ELT, Ariel, and other observatories will enable cross-validation of findings, drastically reducing uncertainties and minimizing the risk of false positives. Smaller, specialized instruments will also play a role. For example, high-dispersion spectrographs on ELT-class telescopes can measure Doppler shifts in the absorption lines of atmospheric molecules, allowing scientists to detect winds, rotation rates, and vertical mixing in K2-18b's atmosphere. These insights are crucial because atmospheric dynamics affect how biosignatures like methane or DMS are distributed and whether they accumulate to detectable levels. The synergy between space-based and ground-based observatories is particularly important. Webb excels at observing the infrared signatures of molecules, while ELT-class telescopes can target complementary wavelength ranges, including the optical and near-infrared. Together, these tools provide a comprehensive spectral coverage, improving confidence in the detection of key gases and enabling detailed modeling of the planet's atmospheric chemistry and structure. Furthermore, upcoming telescopes offer the possibility of directly detecting the thermal signature of oceans or even constraining the planet's surface or cloud properties. While we currently infer the presence of deep oceans from atmospheric composition and models, future observations might provide stronger evidence by detecting heat patterns or spectral features indicative of water-rich layers beneath the hydrogen envelope. In essence, the search for life on K2-18b is not a one-telescope endeavor. Webb has opened the door, revealing tantalizing hints of water, methane, carbon dioxide, and possibly DMS. The ELT and its sister observatories will walk through that door, probing the planet in ways Webb cannot, confirming tentative detections, and adding new dimensions to our understanding. Together, these observatories mark the beginning of a new era in exoplanet exploration, one where the detailed study of distant worlds, including their potential for life, becomes a realistic, methodical scientific endeavor. Discoveries like those surrounding K2-18b don't just excite scientists, they capture the imagination of the entire world. The idea that a planet 120 light-years away might host water, methane, and even potential biosignatures resonates deeply with our innate curiosity about whether we are alone in the universe. Headlines about 99.7% chance of life or the possible detection of molecules like dimethyl sulfide ignite conversations that span classrooms, living rooms, and social media feeds, reminding us that the cosmos is not just a distant backdrop, it's a place full of mystery and possibility. Public excitement thrives because these discoveries are relatable and aspirational. Water, methane, and oceans are concepts people understand, and when framed as hints that life could exist elsewhere, they stir a profound sense of wonder. From a young student imagining alien oceans teeming with microscopic life, to science enthusiasts pondering the mechanics of Hycean worlds, K2-18b becomes more than a distant in the sky. It transforms into a symbol of humanity's quest for knowledge. This imagination is not idle. It inspires engagement with science, from astronomy clubs and online forums to citizen science projects where ordinary people can help analyze exoplanet data. Popular culture amplifies this effect. Movies, documentaries, and novels often draw on real scientific discoveries to construct stories about life beyond Earth. K2-18b provides fertile ground for this kind of storytelling. A hydrogen-rich world with deep oceans, exotic chemistry, and the tantalizing possibility of microbial or even more complex life. The intersection of science and imagination encourages a feedback loop, where public fascination drives interest in science, which in turn fuels more discoveries and inspires the next generation of researchers. Social media plays a particularly powerful role in spreading excitement. Short videos, infographics, and animations about K2-18b allow millions to visualize alien oceans, speculate about possible life forms, and grasp the significance of Webb's observations. These platforms turn abstract data points, absorption lines, spectra, hydrogen atmospheres, into stories that people can relate to and share. For example, a simple illustration of microbial life in K2-18b's oceans or a graphic comparing its atmosphere to Earth's can make complex scientific findings accessible and emotionally resonant. Public enthusiasm also has tangible effects on the scientific enterprise. Funding agencies, policymakers, and universities pay attention to what captures the public imagination. When people care about exoplanet discoveries and the search for life, resources are more likely to flow into telescopes, space missions, and research programs. In this sense, the excitement generated by K2-18b isn't just cultural. It can actively accelerate scientific progress, supporting the tools and teams that will refine our understanding of distant worlds. Moreover, this excitement fosters a collective sense of wonder and perspective. Learning about K2-18b and its potential habitability encourages people to think about humanity's place in the cosmos. Are we the only life forms in a vast universe, or are there countless planets where biology has taken hold? The possibility that alien oceans might harbor life, however microbial, sparks reflection on what it means to be alive, how ecosystems function, and how fragile life is on our own planet. In this way, discoveries like K2-18b are not just scientific, they are deeply philosophical. Public fascination also motivates education and outreach. Teachers can use K2-18b as a concrete example to explain atmospheric chemistry, exoplanet detection techniques, or the methods of the James Webb Space Telescope. Science communicators can illustrate concepts like the habitable zone, Hycean worlds, or biosignatures using real-world data. This connection between cutting-edge research and public understanding strengthens scientific literacy and encourages young people to consider careers in STEM fields. Finally, the excitement underscores a universal human trait, the desire to explore the unknown. K2-18b embodies the dream of discovery, the chance to answer questions that have captivated humanity for centuries. Are we alone? What forms could alien life take? Could we ever visit or communicate with distant worlds? Even though K2-18b is 120 light-years away, its study bridges the gap between imagination and reality, showing that our quest to understand the universe is advancing at an unprecedented pace. In essence, discoveries like K2-18b fuel public imagination, inspire education, drive scientific funding, and connect people to the bigger questions of existence. The thrill of imagining alien oceans, strange microbial life, and chemical signatures of distant worlds is a reminder that science is not just a technical endeavor. It is a profoundly human one, capable of inspiring wonder and curiosity across generations. While the discoveries surrounding K2-18b are undeniably thrilling, it is essential to emphasize the principle of scientific responsibility. In the excitement of detecting potential biosignatures, water vapor, methane, carbon dioxide, and even the tentative signals of dimethyl sulfide, there is a temptation, both in media and in popular discussion, to overstate the likelihood of life. Scientists, however, must balance enthusiasm with caution, carefully framing findings so that the public understands both the potential significance and the uncertainties. One key reason for this caution is the nature of scientific inference. When observing exoplanets, astronomers rely on indirect measurements, such as transit spectroscopy, rather than direct sampling. While Webb's instruments provide unprecedented sensitivity, the data can be ambiguous. Absorption lines might be faint, overlapping, or influenced by atmospheric dynamics, clouds, or instrumental noise. Scientists are acutely aware that preliminary signals can be misleading, as seen in past claims, such as the debated detection of phosphine on Venus. By maintaining careful language, researchers prevent misinterpretation and preserve the integrity of the scientific process. Communication is also central to scientific responsibility. Bold headlines, such as 99.7% chance of life on K2-18b, may grab attention, but they risk conveying certainty that simply does not exist. In reality, this figure, if mentioned at all, is a highly speculative interpretation of preliminary chemical signatures. Responsible scientists explain that detections of molecules like DMS are consistent with potential biosignatures but not definitive proof of life. This nuanced messaging helps prevent public disappointment if later observations revise initial conclusions. Transparency is another vital aspect. Scientists disclose uncertainties, alternative explanations, and the limitations of current data. For K2-18b, this includes considering abiotic sources of methane or DMS, the effects of high-pressure hydrogen atmospheres, and the challenge of distinguishing overlapping molecular features. By clearly outlining these uncertainties, researchers provide a more accurate picture of what is known and what remains speculative, ensuring that excitement does not translate into misinformation. Collaboration and peer review further safeguard scientific integrity. Multiple research teams analyze Webb's data independently, testing models, cross-validating results, and submitting findings to rigorous peer review before publication. This process acts as a safeguard against premature conclusions, ensuring that any claim about potential life is robust, reproducible, and widely vetted by experts. It is through this careful, iterative approach that extraordinary claims, like the possible biosignatures on K2-18b, gain credibility. Public outreach is also part of responsible science. Educators, communicators, and researchers work together to present findings in a way that conveys excitement while preserving context. For instance, graphics may illustrate the presence of water vapor or methane, but captions clarify that these do not constitute proof of life. Analogies, careful language, and emphasis on the ongoing nature of the investigation help the public understand the difference between possibility and certainty. Scientific responsibility extends beyond communication to research priorities. The excitement surrounding K2-18b must be balanced with careful, methodical follow-up observations. Webb and upcoming observatories, such as the Extremely Large Telescope (ELT), will conduct repeated measurements, expand spectral coverage, and explore atmospheric dynamics to reduce uncertainty. Prematurely claiming life without such corroboration would not only damage scientific credibility but could misdirect future research efforts. Finally, scientific responsibility embodies a broader ethical principle. Discoveries about potential life beyond Earth have profound cultural and philosophical implications. Speculative claims can shape public perception of science, influence policy, and affect how society views the search for life. Scientists therefore act as both explorers and stewards of knowledge, conveying findings with integrity, transparency, and humility. In summary, the study of K2-18b demonstrates the delicate balance between excitement and caution. While molecules like water vapor, methane, and DMS hint at extraordinary possibilities, scientists must carefully avoid overhyping results, clearly communicate uncertainties, and rely on rigorous peer-reviewed research. By doing so, they maintain public trust, advance knowledge responsibly, and ensure that when humanity ultimately claims to have found signs of life, the evidence is solid, reproducible, and beyond dispute. The discovery of K2-18b and the detailed observations of its atmosphere mark a turning point in astrobiology, redefining how scientists approach the search for life beyond Earth. For decades, astrobiology was largely constrained by theory and analogues from our own planet. Researchers focused primarily on Earth-like planets, rocky worlds with thin atmospheres and moderate temperatures, or moons in the outer solar system, like Europa or Enceladus, where liquid water might exist. K2-18b challenges these assumptions, showing that habitability may exist in environments previously considered unlikely, such as sub-Neptune worlds with thick hydrogen-rich atmospheres. One of the most significant contributions of K2-18b to astrobiology is the concept of Hycean worlds. These are planets with global oceans beneath hydrogen-dominated atmospheres, which dramatically expands the catalogue of potentially habitable worlds. Previously, scientists often concentrated on planets that were near Earth in size and mass, orbiting Sun-like stars. K2-18b demonstrates that habitability might not require a solid surface, an Earth-like atmosphere, or even exposure to sunlight in the traditional sense. This redefines the habitable zone, extending it to include planets where life could thrive in deep oceans protected by thick atmospheres, thus broadening the scope of the search for extraterrestrial life. The detection of molecules like water vapor, methane, carbon dioxide, and possible dimethyl sulfide also illustrates the importance of atmospheric characterization in astrobiology. K2-18b provides a real-world test case for understanding which chemical signatures can serve as reliable biosignatures in environments unlike Earth's. By modeling how these molecules interact in hydrogen-rich atmospheres and how they might be produced abiotically or biologically, scientists refine the criteria used to assess habitability across the galaxy. This approach moves astrobiology from speculative theory toward empirical science, grounded in observable data rather than Earth analogues alone. K2-18b also influences methodologies in exoplanet research. The use of transit spectroscopy by the James Webb Space Telescope demonstrates that we can detect faint chemical signals from planets tens or hundreds of light-years away. Observations of K2-18b act as a blueprint for targeting other sub-Neptunes and Hycean worlds, optimizing telescope time and spectral analysis strategies. This systematic approach accelerates the identification of planets where life could plausibly exist, guiding both space and ground-based missions. Beyond methodology, K2-18b impacts theoretical modeling in astrobiology. Its hydrogen-rich atmosphere and potential deep oceans force scientists to develop new chemical and climate models for non-Earth-like conditions. This includes understanding high-pressure ocean chemistry, photochemical reactions in hydrogen-dominated atmospheres, and the potential pathways for biosignature molecules to escape into the observable atmosphere. These models not only improve our understanding of K2-18b, but can also be applied to hundreds of similar exoplanets being discovered by missions like TESS, Cheops, and Plato. The discovery also reshapes the prioritization of targets for future study. With thousands of exoplanets already discovered, astrobiologists must decide which ones to observe in detail. K2-18b's combination of a habitable zone orbit, water vapor, and potential biosignatures elevates it to one of the highest priority targets for follow-up observations, guiding the allocation of time on Webb, the ELT, and other future telescopes. It illustrates the principle that even planets unlike Earth can be promising candidates for life, challenging the field to expand its search criteria. On a broader level, K2-18b demonstrates the synergy between observational astronomy and astrobiology. Spectroscopic data, atmospheric modeling, chemical analysis, and habitability assessments converge in the study of this one planet, highlighting the interdisciplinary nature of modern astrobiology. It shows that searching for life is no longer a purely philosophical endeavor, it is a practical, testable scientific pursuit. Finally, K2-18b inspires a philosophical and cultural impact within astrobiology. By showing that life could exist in alien chemical and physical regimes, it challenges Earth-centric biases and encourages the field to think creatively about what life could look like elsewhere. The study of K2-18b encourages researchers to ask not only could life exist here, but also what forms could it take, and how might it interact with its environment. This mindset is essential as humanity expands its exploration to planets with conditions far removed from those on Earth. In essence, K2-18b is reshaping astrobiology by expanding our understanding of habitability, guiding observational strategies, refining models of alien atmospheres, and inspiring new thinking about the forms life might take. It illustrates that life may not be limited to Earth analogues and that our search for extraterrestrial biology must be both creative and rigorous. In doing so, it cements K2-18b's role as a cornerstone in the ongoing quest to answer one of humanity's oldest questions. Are we alone in the universe? Stepping back from the excitement of potential biosignatures and speculative life on K2-18b, it's important to appreciate the big picture. What this discovery represents for humanity's ability to explore and understand the universe. Even if we never confirm life on K2-18b, the very fact that we can detect water vapor, methane, carbon dioxide, and possibly dimethyl sulfide on a planet 120 light-years away is a remarkable milestone in human ingenuity and scientific progress. It showcases how far observational astronomy and exoplanet science have come, transforming what was once science fiction into measurable, testable science. Consider the scale of the challenge. K2-18b is incredibly distant, far beyond the reach of current spacecraft or probes. Detecting its atmosphere relies entirely on interpreting subtle changes in the light of its host star as the planet transits in front of it. That we can not only detect an atmosphere but identify its chemical components, molecules that may hint at life, is a testament to decades of technological innovation, theoretical modeling, and persistent human curiosity. This capability demonstrates that humanity is no longer passively observing the universe. We are actively probing its planets, analyzing their chemistry, and evaluating their potential habitability. The discovery of K2-18b also highlights the power of collaboration and incremental progress in science. From the initial detection by the Kepler mission to the high-precision follow-ups by the James Webb Space Telescope, multiple generations of astronomers, engineers, and theorists have contributed to building the infrastructure and knowledge necessary to make this observation. Each advance, from understanding exoplanet transit techniques to developing infrared spectroscopy capable of detecting faint atmospheric molecules, represents cumulative human achievement. In essence, K2-18b is not just a planet. It is a symbol of our collective ability to reach across space and read the subtle fingerprints of distant worlds. Furthermore, the study of K2-18b demonstrates the iterative nature of scientific exploration. Every observation generates new questions, new models, and new technologies to improve our understanding. By examining its atmosphere, we refine the tools and methods that will allow us to probe even smaller, more Earth-like planets in the future. In other words, K2-18b is both a scientific prize and a stepping stone, a laboratory in the sky that teaches us how to explore planets that we can't visit directly. Its study improves our capacity to search for life elsewhere in the galaxy. Beyond the technical accomplishments, this discovery reflects humanity's expanding perspective of the universe. For centuries, we believed that Earth was unique, that life might exist only on our planet. K2-18b and other exoplanet discoveries challenge this view, showing that planets with potential habitability are not rare curiosities but a common feature of the galaxy. Even if life does not exist there, the very existence of such planets expands our understanding of where life could potentially arise, reshaping our cosmic worldview. K2-18b also emphasizes the importance of patience and careful observation. Detecting signs of life is not about a single dramatic moment. It is about accumulating precise measurements, refining models, and integrating data from multiple telescopes and missions. This methodical approach underscores a larger lesson for humanity. Exploring the cosmos is a gradual, deliberate process that rewards persistence, creativity, and rigor. Finally, the discovery points to future possibilities. Today, K2-18b represents a planet on the edge of our current technological reach. Tomorrow, it may serve as a blueprint for discovering planets even closer in size and composition to Earth, or for identifying unmistakable signs of life elsewhere in the galaxy. It reminds us that the search for life is no longer confined to our solar system. It is an active, global endeavor spanning both space-based and ground-based observatories, international collaborations, and interdisciplinary research. In short, the big picture is profound. Whether or not K2-18b ultimately hosts life, it demonstrates that humanity now possesses the tools, techniques, and imagination to probe distant worlds with unprecedented precision. It reflects centuries of curiosity, decades of technological advancement, and years of dedicated research converging on a single goal: the quest to understand our place in the cosmos. Each molecule detected, each spectral line analyzed, and each model refined represents a step toward answering the most fundamental question of all: are we alone, or is life a universal phenomenon waiting to be discovered? As we reflect on the incredible journey from discovery to detailed analysis, one truth becomes clear. K2-18b is more than just a distant exoplanet orbiting a red dwarf star 120 light-years away. It represents a new frontier in human exploration, a bridge between imagination and empirical science, and a tantalizing window into the possibilities of life beyond Earth. Every molecule detected, every spectrum analyzed, and every model refined brings us closer to answering one of humanity's oldest questions: are we alone in the universe? K2-18b challenges our conventional ideas of habitability, reminding us that life might thrive in forms and environments radically different from our own. Its deep oceans, hydrogen-rich atmosphere, and potential biosignatures push scientists to think creatively about what life could be and how we might detect it. At the same time, the careful, methodical work being done by the James Webb Space Telescope, alongside upcoming observatories like the Extremely Large Telescope, ensures that our conclusions will be grounded in rigorous science rather than speculation. Beyond the technical achievements and scientific intrigue, K2-18b captures the human spirit of curiosity and wonder. It fuels imagination, inspires education, and motivates the next generation of scientists and explorers to look up at the stars with questions rather than answers. Whether life exists there or not, the study of K2-18b teaches us to expand our definitions of possibility, to embrace uncertainty, and to explore the cosmos with both awe and precision. Ultimately, K2-18b may symbolize more than a single planetary system. It embodies the potential of humanity to reach across light years, to detect subtle chemical signatures, and to contemplate life in the most alien of worlds. Each observation is a reminder that the universe is vast, mysterious, and filled with opportunities for discovery. As we continue to probe its depths, we edge ever closer to the profound moment when we might finally detect life beyond our own planet. K2-18b may not just be another planet. It could be the first place beyond Earth where we find signs of life. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.